这个
Is it okay now?
有
Okay. Yeah, so it took us a while to figure it out. Okay. So before we last time we finished the MCMC chapter, and today we are going to talk about the generalized linear models, okay, which actually is follow-up of the linear regression model, okay. But before we get started, okay, a few things to announce. Okay, first, I believe the sample final has been posted. Okay, just want you to be aware. Okay, so that's the first thing. Okay, if you want to know, not exactly like the question that will appear in the final, but like the format of the final exam. Okay, the sample final should give you a hint. Okay, but don't tell me like oh, how come the final questions are different? I mean, that's always like that. Okay, I mean, I try to make like questions different. Okay, every time. So the sample final is the reference. Okay, not something you rely on. Okay, when you prepare for the final. Okay, you can use it as a practice for practice purpose, but yeah, don't expect like the sample final questions to appear in the final. Okay, so that's the first thing. The second thing is that the homework 4 has already also been posted. If I because I sent it out to the TA yesterday, so I believe they already did that. Okay, so the due date is actually let me see, 3 weeks from close to at least more than 2 weeks from now. Okay, so just want you to be aware. Okay, the reason I set it up to be this late is because because of the next reminder, okay, next announcement, which is I will be out of town, okay, for a conference next week, okay. So I will be back, okay, on the 23rd. Okay, so we will have lecture on 24th and the 31st. Okay, May 31st, May 24th and May 31st. We will have 2 additional lectures, and then we have the final exam, and then the presentation. Okay, so this is something I want you to be aware. Okay. I'll be out of town next week, so we, excluding today's lecture, we have 2 additional lectures left. Now, after I come back, okay, on the 23rd. Okay, so if you include today's lecture, we have 3 lectures, right? So how much am I going to cover for 3 lectures? Okay, my estimate is that, okay, this generalizing linear model, the GLM, is one of the most important topics in Bayesian data analysis, which will be covered in about 1.5 lecture. Okay, and the next chapter I will cover is the model comparison. Okay, which because you can model a question, a problem differently. Okay, so which one is more plausible? Okay, the model comparison will give you some hint, but I suspect we will be able to finish that chapter. So yeah, let's see what I can do. Okay, for the model comparison, but and also, okay, I mean, it's if I will only be able to cover a small portion of the model comparison. What I'm going to do for the final exam is that I'm going to exclude that chapter, the model comparison chapter, from the final exam. Okay, in other words, everything that I have covered, from the beginning of the class up to GOM, this chapter will be covered in the final exam, but probably not the model comparison. Let's see how it goes. Okay, if I'm able to finish the model comparison, which is very unlikely, then I'll put it in the final. But if not, if I'm only going to cover just a little bit, well, let's play by ear. Okay, so back to the generalizing linear model. Okay, from the name, okay, of this chapter, you can immediately get the idea. Okay, this is extension of the linear model. Okay, and we talked about the linear regression. I mean, that was the chapter before the MCMC. Okay, by the way. Okay, so when I say in the last chapter, I'm referring to linear regression. Those linear regression model. Okay, we use a linear combination of input variables to predict the mean and output variable. Okay, if you still remember, okay, we do that for quite a few questions. I mean, we cover simple linear regression, we cover multiple linear regression. Okay, so after we get the combination, linear combination of the input variables, okay, as like a mean, okay, we will assume that's like a Gaussian distribution, the mean of the Gaussian distribution, okay, and we are using Gaussian, okay, for to approximate, like to fit like the data basically. Okay, and but this is like the nature of the linear linear regression model. But obviously, okay, you don't have to use Gaussian, right? In different situations, maybe some other type of models, other type of distributions will be more feasible. For example, okay, remember like in the linear regression chapter, instead of using linear regression, okay, we use a student's t-distribution in case if there's some outliers. Remember the SCOMP quartet data set. Remember there's like very good like data set, but there's a one point that's like obviously an outlier. If you have that data set and you apply the Gaussian, okay, distribution, it doesn't work very well. But if you replace Gaussian with a student t-distribution, it gives us a very satisfactory result. Okay, so in this chapter, we are going to explore that direction. Okay, we'll see more examples where it is wise to use distributions, other than the Gaussian distribution. Okay, actually, okay, if you want, we can consider. We say that's a general motif. Basically, it's a pattern. It's a more general form. Okay, that can summarize a lot of different type of models. Okay, including the models that we covered in the linear regression models, like in the last chapter. Okay, so what is this? Okay, it's something like this. Okay, so the core idea, okay, is basically, okay, we first compute the linear combination of the features, which is alpha plus x beta, right? In here, the x could be a matrix, and the beta obviously could be more than one coefficient, okay? It depends on this is a simple regression or multiple regression, okay? So in the previous chapter, if you remember, okay, we just let this linear combination to be mu, right? And then we assume this mu is a mean of a Gaussian distribution. That's what happens in a linear regression models, right? But now, okay, here, okay, we first assume, okay, alpha plus x beta, this linear combination, okay, we can apply a function f on the result, and then assign that to mu. Okay, this f, okay, in the previous chapter, in the linear regression model, this f is actually an identity function. Okay, you guys know what identity function is, right? I mean, in identity function, if the input is x, the output will be the same thing. Okay, basically, I mean, it doesn't change. Okay, so if it's identity function, obviously alpha plus x beta. Okay, well, the result is alpha plus x beta. Mu just equal to alpha plus x beta, which is exactly what we have in the previous chapter, right? So, but now, okay, because we are considering more general form, so we could apply a function f on this linear combination before we assign it the result to mu. And this f, okay, the technical term of this function f is called inverse link function. Okay, inverse link function. Okay, you may wonder how come it's inverse. I mean, you can probably say, oh, you could call it link function, but why inverse? Okay, we will get to that point later. Okay, so first, for this inverse link function, okay, there are many possible assignment. Okay, as we will see. Okay, depending on our purpose, we can use different functions. But obviously, the identity function was the one that was used in the previous chapter. Okay, so the identity function may not be very useful. Okay, but it allowed us to think of several different models in a more unified way. So once we write this the formula like this, it allowed us to unify not only what we are going to cover, but also the linear regression model. Okay, because function f can be explained as like a identity function. Okay, and then okay, why not just call this f link function? And I mean, to call it inverse link function seems to be a little bit awkward. That's actually because, okay, do we have I'm not sure. Okay, good. That's because mathematically, okay, what usually happens is that we apply a function to mu to obtain the result, that is the linear combination of alpha plus x beta. Okay, and we call this g, we call this function g link function. Okay, this is what we normally do mathematically. Okay, but obviously, okay, once we, now we are writing it in an inverse manner, right? This function f obviously is an inverse function of this g, right? And this g is called link function, so that's why that function f is called inverse link function. Okay? So, just want you to understand where this notation comes from, okay? So, why we want to generalize that formula, okay? Why do we need to apply a inverse link function, okay, before we assign the result to mu? That is because sometimes we want to do the some problem, okay, which has a very different nature to the general regression. Okay, for example, okay, if you want to work on a categorical variable, okay, what is categorical variable? Classifications. Okay, classifications. For example, okay, you want to use like certain features to predict, okay, a certain color, such as blue, white, green, okay, or you want to use certain features, for example, the height, the weight, okay, to predict, okay, or to regress, okay, the gender. Okay, gender, it could be male, it could be female, right? So in those cases, the result, okay, will not be a number that is arbitrary, in arbitrary range. So, or there are other examples, biological species, political party affiliations, all these variables, okay, cannot, okay, be modeled by Gaussians because they are categorical variables, right? So, in principle, Gaussian works well for continuous variable, okay, which could have a value on any could have a value. I mean, take a value from like a real line, from the real as long as the result is a real number. So, while the variables mentioned here, okay, are discrete, okay, because they are categorical, they are classifications, right? So, n only take a few values, okay. For example, red, green, blue, okay. Well, I mean, in the categorical variable, I mean, you normally have a limited number of classes, right? Okay, so if we change the distribution, we use to model the data, we will in general need to also change how we model the possible values for the mean of those distributions. So this is like a, something we need to keep in mind. So for example, okay, if you use a binomial distribution, okay, like throwing, like flip coins, we use that. The example we use in the thinking probabilistically and programming probabilistically. I mean, we use the coin flip examples, right? I mean, we use a binomial distribution, okay? So we will need a linear model that returns a mean value in the range of 0 and 1, right? Because the result, okay, of the linear combination of the variables, the input, okay, or features, okay, will be explained, will be considered as like the probability that the coin flip come up head, right? So the probability that coin flip come up head, I mean, that's a probability. So that probability obviously range, is in the range of 0 to 1, right? So, I mean, by the way, for a fair coin, it's more likely that the probability is going to be 0.5, right? We know that, okay? So there are some, limitations. There are some restrictions for this, linear combination of variables. So we need to be able to use, for example, inverse link function to restrict the output to the desired, constraint. Okay, in this case, it's a desired interval, like between 0 and 1. Okay. So the one that we use, okay, to restrict to the range of 0 and 1, okay, is not restricted to discrete variables. Okay, we may want to model data that can only take positive values. Okay, and in that case, okay, you can use like a distribution that will only give you positive values. For example, like gamma or exponential. Okay, this distribution, no matter what value you feed to it, okay, it will always give you a possible value. Okay, so this is like another example that you could have like a different inverse link function. Okay, but okay, and one note that I would like to point out. Remember, we used we just mentioned color as a categorical data, right? Yeah, I mean most of the time we consider color as like a discrete result. Okay, it's categorical. Okay, but color can be explained into different wavelengths, right? Okay, in physics, okay, for example, okay, if you consider, the wavelength such as 650 nm and 510 nm, okay, each of them represent different color, right? So in other words, okay, a value, okay, even for color, okay, you could explain it as a discrete, as a categorical variable. Or if you try to, model the color by the wavelength, then because wavelength is a continuous, value, obviously, right? So yeah, I mean, you could consider color, okay, the same, variable as a continuous variable. Okay, so which one to use? Okay, it's really up to you. Okay, there's no restriction like you have to use like a variable, okay, as a categorical one or as like a continuous one. Okay, it depends on how you model a problem. Remember, okay, for the same problem, you have different ways to model it. Of course, I mean, these different models may not be, all good. Okay, some may not be that good. Okay, some may be better. Okay, when we talk about the model comparisons, we will you will find like how we can compare, I mean, different models. But for now, okay, I just want to point out, okay, for a variable, okay, whether or not it's a categorical or a continuous, it really depends on how you model it, okay? And if you want to model, or if you want to, convert a value, okay, to a range between 0 and 1, okay, into the range of 0 and 1, okay, then the inverse link function that you would like to use, okay, in general is logistic function, okay, and such regression is called logistic regression. And the situation where you want to convert the linear combination of variables into the range of 0 and 1, most likely it's because just like the coin flip, right? I mean, we want to convert the result into 0 and 1. And the theta, what does the theta? What is the nature of the theta? It's a probability, right? It's a probability. I mean, so the same thing applies here, okay? You basically want to, how should I say, like, want to deal with a problem that's like, yeah, we are dealing with a categorical problem, but this is a binary classification. Binary classification, okay, because as I said, it will output probability, right? Okay, once you apply the logistic, okay, function to your linear combination of the variables, the result will be in the range of 0 and 1, right? So it is a probability. So if it's a probability, you can explain that probability as if you have two classes, and assuming these two classes are exclusive, meaning, okay, if the result is A, it wouldn't be B. Okay, if it's a B, it wouldn't be A. Okay, if the result is like exclusive, then okay, you can say that the probability, okay, that come out of this logistic inverse link function is the probability that the result is the positive class. Okay, so this is like how we consider this. Okay, you know, and first, like, you know, no matter what you are talking about, like you are talking about the linear regression models that we cover in the last chapter, or the logistic regression that we are going to, the example that we are going to talk about, they all belongs to the supervised learning in machine learning field, okay? Because like in some sense, we are trying to use the known result, okay? We know the training, the result of the training set, okay? And we use that the training set to train a model, and we use that model for prediction, okay? So because the training set, okay, you know, the instances in the training set has like we know the answer to each of them. So this is considered as a supervised learning. Okay, in the supervised learning, basically we find a mapping between the output and the input variables. Okay, that's the concept of like supervised learning. Okay, and as for like this point is like you know, sometimes the name may be a little. Excuse me, what happened? 喂？
你好，我这里是中立的波波凯陶汽车必须位。
我知道，我在上课，对对对，不好意思。
大概11点会好。
OK，好，谢谢，好，拜拜。
要麻烦您带印章过来盖和解除哦。
OK，好，拜。
好，谢谢，拜拜。
Yeah, sorry about that. Okay. So sometimes, as I said, like some names are not exactly what it meant, okay, or like it may be the name may seems a little bit misleading, okay, because the author, I mean, intentionally give an example, okay, because I mean they are, I believe they are Mexican, okay, or like Spanish people, okay. I mean, there's a dish called sopa seca. Okay, if you directly translate that name, it's called dry soup. Dry soup. If you consider this name, that's interesting, right? Because you know the soup must be liquid, right? I mean, when a soup is dry, how can you drink it, right? So you know, but you know, this name, okay, maybe sounds like a misnomer. Okay, misnomer just like a incorrect name, okay, or oxymoron. Oxymoron just means it's contradiction, okay. But anyway, okay, I mean, if you understand how this dish is prepared, I mean, then we can understand how why it is called this dry soup. Okay, same thing applied for like logistic regression, because you see this term logistic regression. I mean, logistic. Okay, this part means like we apply logistic function in for the inverse link function. So we know that, but regression normally is used to for a numerical result, because we regress to a number. Okay, in mathematics, this is like normally how we call it. Okay, I mean when you have a regression, the result is normally it's going to be a number, but obviously, you know, in this logistic regression, the result is not a number; it's categorical, right? It's a binary classification, right? So, but once you understand, okay, the concept, because we use logistic, okay, on this linear combination, okay, that linear combination can be considered as a regression. So we use this logistic function on the regression, the result of the linear combination, to obtain the probability. Okay, so you know, although we call it regression, okay, it's generally framed as a method to solve classification problems. It's really not to use to solve like a numerical regression problem. Okay. Oh, sorry. So logistic function. What is logistic function? Logistic function looks like this. Okay. You know. So the denominator is 1 plus e to the power of negative z. Okay, where z is the argument. Okay, and the denominator is a 1. Okay, and this value, okay, obviously when z is 0, okay, the result is going to be 0.5. But when z is very large, the result is going to be, you know, when z is large, I mean, this term becomes smaller and smaller, right? So the whole thing will get closer and closer to 1, okay? And when z is negative, then this e to the power of negative z is going to be, larger and larger, and because the denominator is going to be very, very large, so the resulting logistic value is going to be, going to be close to 0. So it's in the range of 0 and 1, okay, and with a mean, okay, at 0.5. If we draw it, okay, it looks like something like this. Okay, when z is 0, it's 0.5. When z is negative, okay, it's getting closer to 0. When z is positive, it's getting closer to 1. Okay, and obviously, the shape of this function looks like an S, right? Okay, so another name that calls the logistic function is called sigmoid. Okay, sigmoid, also known as sigmoid function. That's because, okay, the S shape looking of this function. Okay, so we call it sigmoid. Okay, if you are into deep learning, we normally don't call this function as like a logistic. We normally call this function sigmoid, which actually is one of the earliest used activation functions in deep learning. Okay, but yeah, let's not dive into that direction. Okay, first I just want you to understand this is logistic function. Okay, so we are running out of time. Let's take a 10 minutes break. When we come back, we'll continue our discussion. Okay? Okay. So we could use the this model, okay, this logistic regression model to model the coin flip example that we had in the previous, like in the earlier, much earlier chapters that we used. Remember we used we used that to talk about the conjugate prior, okay, and it is a good example that can be used to explain many different phenomena. But obviously, this logistic regression, as I said, because it can be used for like a binary classification. So if you want to classify, for example, ham, spam, okay, like if an email is a normal email, safe one, okay, we call such an email as a ham. Okay, if an email is spam, it has content like a harmful information, okay, we call such email is spam. Okay, so the email can be classified into ham and spam, or safe, unsafe. Okay, obviously this is for like a certain like safety situation. Okay, and the cloudy, sunny. Okay, this is for weather forecast, and the healthy, ill. This is for like a diagnose. Okay, the health diagnose. Okay, or hot dog, not hot dog. I don't know what that is. Okay, obviously, the author is trying to make a fun of this thing. Okay, because hot dog, not hot dog, obviously is not some binary classification that we can normally see. Okay, but anyway, okay, all this type of like a binary classification can be used. We can use the logistic regression on it. okay, because they take the value, okay, they get a value, of y in the range of 0 and 1, okay, and we can explain it as like the probability of the positive class, okay, and all these can be considered to be associated with like a coin flip example, okay, so so we may remember we use the Bernoulli distribution, okay, as the likelihood, okay, so the difference with the coin flip problem is that now theta is not going to be, generated from a beta distribution. In the previous discussion, okay, we draw like theta from a beta prior, right? But now, instead of drawing theta from a beta prior, we model theta to be the result of a logistic regression. So theta is going to be, okay, this logistic alpha plus x beta, okay, and y is going to be Bernoulli theta. This part is, remains the same, just like what we had previously, okay. So so this is like we change the previous one into, if you want to model it into like a logistic regression, this is how we do it, okay. So instead of using an identity function in the linear regression, we use a logistic function, okay, here, okay, and then, okay, if you, now we also want to consider other examples, okay, such as a famous, example called iris, okay, data set, okay. This iris data set, you know what iris is, right? Iris is one kind of flowers, 兰花, okay, 兰花, okay. So Taiwan is famous for like producing a lot of different kinds of iris, okay, by the way, okay. So this classic data set, okay, contains 3 different species, okay, 3 different species, okay, Setosa, Virginica, and versicolor, okay. To be honest, I'm not very good at those like biological names, okay, species names. But you get the idea, okay. They represent 3 different kinds of iris, okay. So they are our dependent variable, okay. So obviously this variable is categorical, right? We have 3 classes, okay, and we have 50 individual cases of each species, okay. So for each species, we have 50 entries of data, okay, and the data set contains 4 variables, okay. We can use them as independent variable, okay. So it includes petal length, petal width, sepal length, and the sepal width, okay. So petal is the 花瓣, okay, okay. It's like the part of the flower, okay. I don't know how to. A flower has like some. I don't know how to explain petal without using petal, okay? But if the so flower usually look like this, right? You have flowers, okay, and right, and so this is petal. Okay, this is petal. And the sepal is like this. This is sepal. Okay, so 花萼. Okay, but you get the idea. Okay, the petal and the sepal. Okay, so you can measure the petal length and petal width, and the sepal length and the sepal width. So you have like these 4 features. Okay, so we can load data frame with iris data set. Okay, this is very simple one. Okay, just read the CSV file. Okay, and you can use the head function to list like the first few entries of this data set. Obviously, the first few entries all belong to the Setosa class. Okay, and each entry has like a different sepal length, sepal width, and the petal length, petal width. Okay, so if you plot the 3 species, okay, versus sepal length, okay, I mean just using one feature, okay, we can use a strip plot function. It looks like something like this. So you can imagine, okay, from this figure, okay, Setosa has, in general, has the shortest sepal length, right? And Virginica, okay, in general has like a longest sepal length, right? I'm not saying like they are completely separated, because like obviously some Setosa sepal length is even longer than some Virginica sepal length, such as this one. This one, I mean, it belongs to Virginica, but it happened that, I mean, this instance has a very short sepal length. And some of these Setosa instances, I mean, has obviously a longer sepal length than this one, right? But I'm talking about the overall, okay, in general speaking, okay, Seto class has the shortest, Setosa class has the shortest sepal length, and then it's a versicolor, and then it's the Virginica has the longest sepal length, right? You can tell from this figure, okay, and yeah. I mean, obviously you can choose, okay, different plots, such as violin plots, okay, or like, this one also explain like what they mean by the, here, okay, we use jitter equal to true. Okay, if you don't use jitter equal to true, okay, I mean, jitter equal to true, it's going to try to plot this point, with a little bit of different x, coordinates. Okay, if you don't set jitter to be true, okay, if you set jitter to be false, then what happens is that all these points will be collided into one single x coordinate value. Okay, so it's really not, I mean, well, because like a lot of them are too close. So what should I say? Like for example, like these few points, they will be collapsed into only one. So it's more, it's difficult to observe like the whole population distribution. Okay, so that's why like the author used like set the jitter to be true. Okay, I mean, and you can use other plot like a tool such as the violin plot, available as, with Seaborn. We actually draw the violin plot, in previous examples already. So, I will not. This one is another way to inspect the data by doing a scatter matrix with the pair plot function. So this is one interesting way to visualize the data. Let me show you the result. Maybe it's more interesting. Okay, first, okay, we have 4 different features, right? We have 4 different features. We have sepal length, sepal width, and the petal length and the petal width, right? So for each, for any pair of them, okay, basically C4, okay, you get 2, okay, for comparison, okay, so total will be, 6, okay, 6 different pairs, okay. So you can, for example, this one represent the sepal length versus the petal width, okay. So you can, it plots the distribution of them, okay. Of different species, okay. The blue and the orange and the green indicate different species, okay. And this one indicate like the sepal length versus the petal length. So each one you can, for each instance, you can, once you have 2 features, you can plot a dot, right? That's obvious the case. For each instance in all these 3 species. So, and obviously, okay, in this example, okay, because of the nature of this matrix, okay, for example, this one is identical to this one. Of course, like the difference is that like you need to change the angle, okay. But basically, they, for example, this one represent the same figure. This one represent the same figure, and so on. Only 6 of them are useful. Only 6 of them are useful. When it comes to like, checking out like the correlation of 2 different features. Okay, and for the diagonal cases, okay, because the diagonal one, okay, if you still draw like for example, like the sepal length versus the sepal length, it doesn't make sense, right? It's going to be 100% correlated, right? It's not going to give you any useful information anyway. So, okay, instead of doing that, here we set diagonal kind to be KD, so you will draw the kernel distribution of like a different species for that particular feature. Okay, so this is one interesting way to visualize data. Okay, you can do this pair plot. Okay, so then so we are going to do this simple classification problem. Okay, we start with 2 classes because, well, remember we are going to use like a logistic regression, right? Logistic regression applies only to binary classification. So unfortunately, in this data set we have 3 classes, right? So we will only pick like 2 classes out of these 3, okay, to as an example to do it, okay. So, you know, so we pick the setosa and the vesicolor. Okay, the setosa vesicolor, and then we use like a sepal length. We use a sepal length. Okay, so we use only one. I mean, out of the 4 features, we use only one feature, sepal length, and out of 3 classes, we only pick 2. Okay, the reason we pick 2 is because, I mean, right now, the model, I mean, the that logistic model can only, I mean, you know, solve the binary classification. Okay, so first we set like we get like a setosa and the vesicolor and save that the information in the data frame. Okay, and you know, we try to centered the data set. Okay, so then okay, here, okay, we have like the alpha is like you know, we draw it from the normal distribution with a mu 0. Okay, because we already centered those like feature. So mu is 0. Standard deviation is 10. And the beta, I mean, is mu is 0. We draw it from normal distribution with mu, the mean 0, and the standard deviation 10. By the way, standard deviation 10 means like this is a very vague prior. Okay, we don't put like a lot of like a very strong prior to it. Okay, and then mu equal to this mu is you know, is the linear combination of like of the variables. Okay, so it's going to be alpha plus the math dot x c x underscore c. Okay, and the b x underscore c is it comes from the data. Okay, and then then we use like you know, here. Okay, we apply this pm dot math dot sigmoid. This is one way to call upon the logistic function. Okay, this just means like we are calling like the Thanos logistic function. Okay, then we apply that logistic function on mu. Okay, the linear combination. Okay, and we assign the result. Okay, to theta by using deterministic. Okay, so this result is going to be applied to, to be assigned to theta, and then this BD is a boundary. Okay, boundary is negative alpha divided by theta. What this means, I will explain. Shortly. Okay, and then we try to fit this p equal to theta, observe equal to y0. This is obviously like from the data. Remember, we are doing this the supervised learning, right? So then we generate like 1,000 samples. Okay, so that's it. Okay, so this pm.math.sigmoid. Okay, just an alias for the Thanos function with the same name. Okay, so you could spell out this sigmoid or like a logistic function by yourself. It's going to be the same anyway. Okay. So that's like generate the plot. Okay. So we omit here. We omit some like a trace plots that we usually like show, but because those like are really like not that important. But we can show you. Okay, this one. Okay. Here is like okay. You have like a different sample length. Okay, for the instances, and the blue indicating indicates like this instance belong to, I believe it's like the negative class, meaning the class is, eventually assigned to be 0, okay, and which is, I believe, is like setosa, and the other instances here are this color, okay, the orange ones represent this color. Remember, I told you this color has a longer sepal length, overall longer sepal length than the setosa. Okay, I mean, of course, there are some overlap. You can see there are some overlap. Okay, but there's like a decision boundary. Okay, decision boundary, like and then this is like this green line represent like a value, okay, of the sigmoid or like a logistic function, okay, and the dark green line indicate like okay, that's like we use the mean that of the posterior. Okay, if you use the mean of the posterior, you only draw one line, right? But this one, this band of like a logistic regression just shows like a 94% HPD. Okay, and this is like shows like the place that you have like the value is like 0.5. I mean, from this like the logistic function, okay, because like if the result is higher than 0.5, we assume it's this color. If the value is lower than 0.5, we assume this instance is going to be setosa. Okay. So this way indicate like what value. I mean, we normally what value of the sepal length is going to be mapped to 0.5. Of course, like it also contain like a range. Okay, 94% HPD range. Okay. After we are talking about distribution. Okay, and remember like yeah, I already explained this. Okay, so remember like we talked about this one. So what is like negative alpha divided by beta? Okay, because this is our logistic regression function, right? And we know logistic regression function. Okay, we assign. We will. Remember, like I told you, like the place to determine. Okay, the result, the instance belong to one class or the other is is like 0.5, right? 0.5. If you plug in 0.5 equal to this one, you immediately get that. Okay, because logistic is like logistic function looks like this, right? So when will logistic function give you 0.5? Remember what I told you? It's when z is 0, right? When z is 0, you get 0.5, right? Okay, and z is the argument, right? So, okay, so this argument, when this one is 0.5, it means this argument is 0, right? So when this argument is 0, when will that happen? It will happen when your xi equal to this one, right? Very simple math, right? Very simple math. Okay, so this one indicate the boundary decision. Okay, the boundary of a decision, like when to determine, like a class is like it's a positive class. When to determine a class is negative class. Okay, so this value of theta is like a p probability. Given the data, probability of y equal to 1, the positive class. Okay, probability. Okay, so in this sense, the logistic regression is a true regression. Okay, the key detail is that we are regressing in the probability that a data point belongs to a positive class. Okay, given a linear combination of the feature. So yes, you could, eventually, okay, you can understand why we call it logistic regression, why we have that regression term there. Okay, once you understand the whole, the meaning of like, what we are doing here. So it's just like, remember that dry soup example. Okay, I believe that dry soup example must be like they put a lot of ingredient and then cook like for a long time to vaporize most of the liquid to create that dry soup. So that's why they call that dry soup. I don't know because I never had that dish, but my guess is something like that. Okay, but anyway, okay. So we are modeling this mean of dichotomous variable. Okay, dichotomous just means like a binary variable. Okay, so that is number in the range of like 0 and 1. Okay, so then we introduce a rule to turn this probability into a two-class assignment. So basically, like if it's greater than 0.5, okay, the result is greater than 0.5, we assign positive class. Otherwise, we assign negative class. Okay, so do we have to use 0.5 for this boundary? The answer is not necessary. The 0.5 is really not a magic number. Okay? So when we use 0.5, okay, it implies that okay, it is okay to make a mistake in either one direction or the other. Okay, so it will be the same to us to misclassify a setosa as a Vesicator or Vesicator as a setosa. That's fine. Okay, if that's the case, because we are not in favor of any, positive class or negative class. So it will be nature to put 0.5 as a boundary. However, this is not necessarily always the case. Okay, sometimes like misclassify one way, okay, may cause much more than misclassify the other way around. Okay, for example, okay, let me use a project that I had with ITRI as an example. Okay, I used to do a project with ITRI to identify, to classify. Okay, if there's some car or motorcycle that trespass, how should I say, trespass in front of it's not MRT, it's轻轨英文怎么讲 ？Monorail, you know the monorail, right? Okay, in some like in Kaohsiung, I don't know if you are from south part of Taiwan, in Kaohsiung we have those type of monorail. That's really not monorail, but that's kind of like a train that is running in the city, right? okay, and you know, we what we did is like we try to use a radar to detect if some car or some motorcycle will, you know, will because sometimes some vehicle will, you know, even though it's red light, they will still like run through it. Okay, so I mean before the train comes in, okay, we do the classification to identify if there's such an event. If there's such an event, the train driver will have to, you know, hit the brake to stop the train, obviously. Otherwise, it's going to be, you know, fatal traffic accident, right? So in this case, okay, if you I mean, this is going to be a binary classification, obviously, right? Okay, either there's like a trespassing or there's no trespassing, right? So this is a binary classification. Okay, but in this case, misclassification, the impact will be huge. I mean, will be very different. Okay, if you incorrectly classify you know, not trespassing case into trespassing, then yeah, I mean, well, you inform the train driver to hit the brake to stop the train. Well, it's going to be inconvenient to the train driver and the people riding the train, obviously. But at least nobody gets hurt, right? But if you misclassify a trespassing into non-trespassing, then, as I say, like if the train like runs through that, I mean, in that situation, most likely it's going to create a fatal car accident, okay, which is like you know, has a, you know, very bad, very big impact. So in this particular case, okay, misclassifying one way is much more costly than the other way around. Okay, so this misclassification does not need to be symmetrical. Okay, in the case that I mentioned, obviously it's not symmetrical. So in that case, you may want to, you know, set this value differently. Okay, you may want to set this value differently. Okay, so as you you know, may remember from program probability, okay, when we discussed loss function, I mean that's a different issue, but I already gave you an example. Okay, the example that we went through is a logistic regression, obviously, but that was a simple logistic regression in the sense that we only use one feature, right? We only use one feature, the sepal length, right? We use only the sepal length. And we could, you know, basically, you know, consider multiple logistic regression as well. I mean, the multiple logistic regression is just like a multiple linear regression. Okay, it is the case when we consider, you know, multiple features. Okay, multiple features. So, okay, multiple logistic regression is about using more than one independent variables. So let's try combining the sepal length and the sepal width. Okay, sepal length and sepal width. So, and we also need to pre-process the data. Okay, so basically, like, yeah, we get the value, and then, okay, so in this case, okay, now we have two features, right? So let's consider the same situation, okay, that we want the boundary to be 0.5. In this case, okay, if you're reordering, okay, you will find that the value of x2 for which theta equal to 0.5 will be corresponding to this following equation. Okay, if you look at this one is obviously, you know, a line, right? A line. The previous one, this one is a point, right? This one is a point. So if you have like one feature, the decision boundary is going to be a point. If you have two features, the decision boundary is going to be a line. Okay, so this is very natural because you are, you are restricting this decision by a linear combination. Okay, so so if you try to extend it to n features, okay, if you try to extend it to n features, you will find that the boundary will be n minus 1 a formula, okay, n minus 1 linear formula, okay, so it will be generally a hyperplane, okay, so actually like if you consider like a one dimension, okay, or I mean one feature, okay, its hyperplane is a point. If you consider two dimension, okay, two features, the hyperplane is going to be a line, which is, which makes sense, okay, so it's a hyperplane, okay. So we can implement this model, okay, which looks almost identical to the simple logistic regression one, okay. The only difference is that, okay, the beta, okay, the shape is the length of x, and which we have in this case we have two different features, okay, and then okay here we use the matrix multiplication, so it's going to give you like I mean the linear combination of alpha plus like x beta, okay. We will assign that to mu, and now if you look at here, okay, we still use deterministic, but now instead of calling the Thanos sigmoid function, we spell out the logistic function here, right? As I said, they are identical. I mean, if you want to use anyone, I mean, you will end up with the same thing. Okay, anyway, okay, so so you get, I mean, you apply the logistic function to get a theta, okay, and the boundary is going to be this one, okay, this one which is this one, okay. The reason to keep track of this is because eventually we want to generate. We want to generate like the posterior of this boundary, okay, so that we can generate like a 94 like a PDF for this boundary, okay, and then okay we fit like the result and try to generate 2,000 sample, okay. So you can plot the data and the decision boundary. It's going to be look like this. So boundary is going to be a line, something like this. Okay, and if you observe this black line is created by the average of the posterior. Okay. So that's why it has a single line. As for like why this 94% like HPD doesn't look like it has like a same width all the way. It's because like 这些东西 are not necessarily the same slope. Okay, they actually like somehow like a pivot. I know. They will go through roughly the average of the x and the y. Okay, so with a slightly different slope, so that's why it creates this kind of like a, it's wider on two ends, narrower, I mean on at the center. Okay, and you can see that okay, this result classify these two classes pretty well, right? It classifies these two classes. There's perhaps a little bit of, you may misclassify these few points because they are actually, very close to, already inside the boundary of the decision boundary. They are already inside the decision boundary. So they may be misclassified. But at least, okay, you can see, you can tell that, this classification it works for most of the cases, right? Okay. So, I think I already explained it. So we must be careful when we try to interpret the beta coefficient of a logistic equation. Okay, interpretation is not as straightforward as the linear model. Okay, which we look in linear regression models. Why? Because the logistic the inverse link function, okay, has a long linearity. Okay, that we need to take into account. What do we mean by this? Here, you see, this is the result of like a logistic function, right? So this logistic function, okay, is nonlinear, in the sense that when your feature is getting close to the center, okay, your result change faster than when your feature value is like near the two ends. Okay, so the change happen quickly at the center because obviously you can see the center, the slope in the center is much steeper than the slope at the two ends. Okay, so yeah, when you try to explain like the beta impact of the beta, it's because the impact is not linear. Okay, because of the logistic function. We use logistic function as a inverse link function. So yeah, it's more difficult to explain it. Okay, so if beta is positive, increasing x will increase this p probability that of the positive class by some amount, but we cannot specify that amount very well. Okay, the amount is not a linear function of x. Okay, instead it depends nonlinearly on the value of x. Okay. It depends where you are talking about that x. If it's closer to the center, the change is going to be bigger. But if it's like near two ends, the change is going to be not that much. So we can visualize this fact. I already showed you that slide 18, okay, which shows that logistic function. Okay, so instead of a line with a constant slope, we have a S-shaped line with a slope that changes as the function of x. So a little bit of algebra can give us some further insight into how much p of y equal to just the probability of the positive class changes with beta. So yeah. So this is the algebra that I was talking about. Okay. So we have this theta equal to logistic alpha plus x beta. So we know like we can apply the inverse of logistic. The inverse of logistic. Okay. So if you apply the inverse of logistic, the inverse of logistic is called the logit. Okay, logit is defined like this: log, okay, z over 1 minus z. Okay, so if you apply this logit function on two ends, okay,
on the left hand side is the logit theta, obviously. On the right hand side, because like the inverse function and the function they cancel out each other, so it's going to end up with alpha plus x beta. Okay, and then you can apply, you can write the left hand side into the original form of logit function. Okay, so this 1 minus z, okay, is 1 minus theta. Remember what the theta is. Theta is the probability of the positive class, right? And now we are talking about the binary classification, right? So 1 minus theta is the probability of negative class, right? Right? Okay, if theta is probability of positive class, 1 minus theta, because we are talking about binary classification, so 1 minus theta is the probability of negative class. So interestingly, okay, alpha plus x beta will be the log of probability of positive class divided by probability of negative class. Okay. In other words, okay, we in like mathematics, okay, we call this value. This is theta divided by 1 minus theta. Okay, remember theta is the probability of positive class, right? And so we can write it like this. So probability of positive class divided by probability of negative class. Okay, this quantity is known as the odds. Okay, mathematically, okay, where does this, you guys probably have learned like a probability from, I'm not sure, like from high school or at least like, or like in college, I mean, you learn probability, I mean, but you may not heard of these odds. I'm not sure if you heard of this, okay? But anyway, these odds, okay, in mathematics, where does this concept gets used? It gets used the most in the gambling situation. In the gambling situation, okay? For example, okay, the odds of success are defined as the ratio of the probability of success over the probability of not success. So for example, the probability of getting 2 by rolling a fair die, okay? Because the probability of getting 2 is 1 over 6, right? And the probability of not getting 2 is 5 over 6, right? So if you divide these two amounts, you get 0.2. So that's the odds of your, or one favorable event to 5 unfavorable events. So, I mean, if you like to go to gambling, like a casino or somewhere, this odds is a very convenient way to calculate like the chance of winning, and which is used actually very often. But other than the gambling situation, it actually doesn't get used that often. Okay, but anyway, I mean, because once we can write it like this, it means what? In a logistic regression, the beta coefficient encodes the increase in log odds unit by unit increase of the x variables. So when the x variable increase by 1 unit, okay, when the right-hand side increase by 1 unit, the log result of your odds increase by, by 1 unit as well. So that's why we call it like the increase in log odds. Okay. Yeah. So yeah, I think like let's take a 10 minutes break. When we come back, let's continue the discussion. Okay? Okay, so let's get started. So, so transformation from probability to odds is a monotonic transformation. Okay, in other words, when probability increases, odds increases too, and vice versa. Okay, here, okay, we especially draw a figure to show that fact. I mean, one thing to be careful is that, okay, probability obviously is in the range of 0 and 1, but the odds, okay, is in the range of 0 and infinite. Okay, so because it's a ratio of two positive numbers, okay, but you know, and those two numbers are obviously, you know, one is like theta, one is 1 minus theta. Okay, you can imagine, okay, such a combination, okay, the smallest can only be 0, and where theta is 0, okay, and when theta is close to 1, okay, you get like infinite, okay, so and because it's like in this range, when you know use the log on this range, you get negative infinite to positive infinite, right? So I mean, you know, here it goes. Okay, this blue line shows the log odd. Okay, log odd. Okay, so it's you know, and the sigmoid. This one shows the sigmoid. Okay. Okay, I think, sorry, the blue line shows the odd. So it's from 0 to infinite. And this one, this orange one shows log odd. Because log odd is, I mean, you apply the logistic function to it, so it's like a sigmoid. It's a S shape. So you can see that, you know, no matter which point you are talking about, they increase, you know, together. Okay, even though the amount of increase is not linear. Okay, it's not proportional, but I mean they increase, you know, both increase. I mean, you know, being together. And the value of the coefficient provided by summary in the log odd scale. Okay, log odd scale. By the way, like if you remember, like you know, because we in MCMC chapter, we already cover the effective sample size. We already talked about the MC error. Okay, so now, okay, you know the mean, you know the standard deviation, you know the MC error, you know the HPD 3% to 97%. This basically indicate like a 94% HPD the range of the 94% HPD and the effective sample size. The only thing we haven't covered is this R hat. Unfortunately, we probably don't have a chance to cover that this semester. Okay, so once you try to output this the alpha, beta 0, beta 1, all the variables. I mean the statistic of all these variables. And it looks like this, but these are, you know, in log odd scale. Okay. So one way of understanding the model is to change parameters and see what happens. So in the following block of code, so we are computing log odds in favor of versicolor as log odd versicolor. Okay, I mean, which is like this one. Okay, so and then the probability of versicolor with the logistic function. Okay, So we repeat the computation by fixing x2 and increasing x1 by 1. So if you try to do that, okay, by using this piece of code, what you are going to get is that, okay, the increase in log R, okay, is about 4.66, okay, if you run this piece of code, okay, and this is, close to the value of beta 0, okay. The beta 0 is 4.65, so which tells you that, okay, if you increase the, in log R, okay, it's going to result in like, the increase of 1 beta 0 value. I mean, well, it's not exactly the beta 0, okay, but it's a number very close to beta 0. The reason because, they are different, it's just because of like, we are talking about this, it's statistically, okay, they are very close. It's just because like, we're talking about like a posterior, it's a distribution. So after all, it has something to do with like sampling. So sometimes it's a little bit slightly different, but the difference is almost negligible, okay, okay. So, so this is in line with our previous finding. The encodes the increase in log R, unit by unit increase of the x variable. So, yeah, so the increase is in the probability, okay, once you, apply the log to it, okay, it's 0.70, okay, so increase of probability is huge, okay, because remember the probability is between 0 to 1. So, just increase like, x1 by 1, the probability increased by 0.7. Okay, that's because it's close to, it actually is close to, because it's close to the middle. So that's why like it increased very quickly, okay? So, one thing also that we also need to know, be careful is that, okay, remember like in a linear regression model chapter, we talk about this, when two features are highly correlated, then it's going to create some problem. I'm not sure if you still remember, okay, because it was like, we talked about that, and then we went to talk about MCMC, now we are talking about this chapter, so maybe some of the content in the linear regression model has been, you guys have have already forgotten, but you can check out like the handout, quickly and to refresh your memory, okay? But anyway, okay, so if variables are highly correlated, yes, it will create some problems. Especially like they are, you will find it difficult to restrict the posterior, okay? The resulting posterior. So it's because like these variables, because they are highly correlated, they are affecting each other. You can even like consider them to be identical, okay? And we talk about this like in a linear regression model, okay? You can check. Again, check out that part. By yourself, okay? Because we are running out of time. I really want to cover, some additional material anyway. So the same phenomenon, okay, will occur, okay, in the logistic regression model, okay? So, correlated data has less power to restrict the model,
Okay, that is why, as I say, the resulting posterior, okay, is going to be much wider. Okay, when there is no overlap between classes, given the linear combination of variables in our model. Okay, so using the iris data set, okay, we can try running model 1. This time using the petal width and the petal length variable. Okay, the reason we use the petal width and the petal length variable is because, okay, you will find that the beta coefficients are broader, much wider than before, and also the 94% HPD, this band in the figure is much wider. First, let me show you the petal width and the petal length. Okay. Where is it? Here. Petal length and petal length and petal width, right? So you can see they are highly correlated. Okay, they are highly correlated. And originally, okay, we use sepal length and sepal width. Okay, so sepal length and sepal width, you can see that, okay, I mean, they may be slightly correlated, but the figure, suggests that, these two values are not that highly correlated, right? Compared with petal width and petal length. This one is obviously, it's much closer to a line, right? It doesn't matter which species you are talking about. Okay, all these points are almost fall on a line. Okay, so obviously the petal length and petal width are very highly correlated compared with sepal width and sepal length. So this one, okay, you will find this band. Okay, if you use if you change to two highly correlated features, you will find this band becomes much wider. Okay, so yeah, this is because if you check out the petal width and petal length, okay, the correlation is 0.98. That's very, very high, right? The correlation is very close to 1, right? But the sepal length and sepal width is only 0.21, okay? Well, it's correlated a little bit, but not much, right? Compared with that 0.98. So this is the issue, okay? So figure on the right, it's a heat map. This heat map basically shows the correlation between different features. Here we only output the absolute value of the correlation. Correlation can range from -1 to +1, right? But here, the way we draw this heat map, we only output the absolute value of the correlation, because after all, we only care about how big this correlation is. If it's close to 1 or close to -1, basically it just indicates these two features are on a line, either this line, this direction, or the other direction, like this. Either way around, it's going to have a very bad impact on the model. Okay. So if that's the case, what do we do?
Okay, one solution to deal with these highly correlated variables is just remove one. Okay, or if you have more than two, okay, you may want to remove like more than one. Okay, correlated variables. Okay, so this is one way. Okay, we talk about this like in linear regression model chapter. So another option is to put more information into the prior. Okay, so this can be achieved using informative prior if we have useful information. So for weakly informative prior, okay, Andrew Gurman, okay, Andrew Gurman is the author of that red reference book, okay, and the STEM team. STEM is like if you are writing if you are using R programming language like for Bayesian data analysis, then STEM is pretty much a standard package for you to use. I mean, it's just like if you use Python, I mean, and the PyMC3 is your tool. Okay, something similar to that. Okay, so the Andrew Gurman, the STEM team, okay, they recommend, okay, this one, okay, scaling all non-binary variables to have a mean of 0, and then use this student t distribution of like mean 0 and the v and the SD. Okay, so SD is like chosen in order to weakly inform us about the expected value for the scale. So as for like this normality variable, okay, v indicate the normality variable. Remember when v is like close to a large number, this student t is going to be close to a normal distribution. Okay, so this v is suggested to be around 3 to 7. So this prior is saying that in general we expect the coefficient to be small, but we use fat tails. Okay, so in case if there's like occasional outliers. Okay, I mean that's what we meant. Okay, so as we saw like in the previous chapters, okay, using student t distribution leads to a more robust model than using a Gaussian distribution. Okay, so yeah, I think like we probably originally I hope to talk about more things. I mean, but now it looks like we can only talk about this unbalanced class. Okay, so the IRIS data set is completely balanced in the sense that each species comes with like 50 instances, right? So it is completely balanced. Okay, but a lot of time, okay, if you you have like unbalanced data. For example, like you get a lot of samples from one class, but not so many from the other class. Okay, so this is something to thank Ronald Fisher for. Okay, because Ronald Fisher is the one who collect like this like IRIS data set. Okay, and Ronald Fisher happens to be the one who promote the use of p-values, okay, which obviously is not what Bayesian data analysis people likes, okay. Unlike his dedication to popularize the use of p-value, but anyway, okay, you get the idea, okay. So on the contrary, many data sets, okay, consist of unbalanced data, as I said, okay. So there are many more data points from one class than from another, okay. So if this is the case, logistic regression can run into trouble. Okay, I mean, what trouble it is? Okay, it's like the boundary cannot be determined as accurately as when the data set is more balanced. Okay, let's look at an example. Okay, so let's still use the IRIS data set, but now let's intentionally remove some data points from the Setosa class. Okay, so here, okay, we still use like two classes, Setosa and Vescaler, okay. But now, if you look at here, okay, we, you know, we try to get the entries after the 45. Okay, after the 45. So in other words, okay, because the first 50 is setosa, okay, and then the next 50 is the Vesicaler. So we try to remove the first 45. So it means what? It means we only keep 5 entries for the setosa, and the other 50 for the Vesicaler remains, you know, in the data in there. Okay, so then, okay, we basically do exactly the same thing. Okay, the other part remains the same. I mean, we already talk about how to do this. So I will hand wave the other part. But what we are going to end up with, okay, I mean, we are still use this one. Okay, we if you output the result, I mean, let's compare this one with the with this one. 2 things you can identify. First, if you look at the middle line, this middle line, okay, in the balanced data set case, it's more in the middle, right? It's more in the middle. But in the unbalanced one, you can see that, okay, instead of keeping this black line in the middle, it's actually closer to the the class with fewer samples, right? Okay, this is the first thing. The second thing, I mean, obviously, this one, okay, we get a much wider 94% HPD, right? Okay, for the boundary. Okay, for the boundary. So for the first one, it's obvious. Okay, so and there's no other way to explain that. I mean, so that's why we say if the data set is not balanced, okay, this boundary decision may have some issue. Okay, may have some issue, and for the second issue, for the second problem, this 94% HPD is going to be wider. Some people may argue, wait a moment, we already have now we have a fewer data point, right? We have fewer data point. Originally we have 50 for one class, 50 for another class. So totally we have 100 data point, right? And now we have 55, right? So almost half of the data point. So since you have, fewer data set, okay, fewer data point in the data set, okay, it's nature for your posterior, okay, 94%, okay, HPD to be wider, right? I mean, if you still remember the basic principle of Bayesian data analysis, I mean, this is nature. Some people will argue, okay, this second issue, okay, that HPD is wider, okay, it may not contribute because it may not be because the data set is unbalanced. It's because you have fewer data points in your data set. Okay, this explanation is also valid. I'm not saying this is not correct. So there's an exercise, okay, that you can use. I mean, you can check out that exercise to see that exercise is pretty much trying to tell you okay, we have roughly, because it's 55, right? So roughly let's have the same amount of data, about 50, 55, but now it's even. And let's see how wide. That's 94% PDF is you can compare with this one and see like, if this is caused by unbalanced data set or not. Okay, and by the way, this is the question that, one of the questions in homework 4, okay? So just want you to be aware, okay? I leave this in homework 4 for you guys. You can try to do it like, yourself, okay? All the codes are there, okay? So you can generate like the figure very easily, okay? So, okay, so how do we make sure, okay, this problem gets resolved? Actually, it's not that easy, okay? The obvious solution is to get a data set with roughly the same data points for each class, okay? If you are the one who collects the data, okay? So this can be important to have in mind if you are collecting or generating the data. If you are the one who is in charge of the data collection, data generation, yes, don't give yourself a trouble, right? Just generate like this data set by yourself, okay? So this is, so that you don't run into such a problem. But, okay, if you have no control over the data set, like a lot of time, you get the data set from somewhere else. So this data set is really not controlled by you, okay? So you should be careful when interpreting the result for unbalanced data. Remember, if it's unbalanced, that boundary will look closer to the minority class. Okay, so this is like something you need to keep in mind. Okay, check the uncertainty of the model and run some posterior predictive checks, and to see whether the results are really useful. Okay, because sometimes like when the result is too biased, it may not be that useful. Okay, so no, if that's the case, like another option will be to input more prior information. You can encode more prior information if available, and run alternative model. You can change the model. For this alternative model, again, like a model comparison chapter may come in handy. Okay, hopefully, like we will have time to talk a little bit about that. So we will explain later in these set of slides. Okay, so anyway, so that's for the unbalanced data. Okay. Well, we have only 10 minutes. I'm not sure like how much we can talk about. So I will just try to start this this new topic, but perhaps like we just like have to stop like short of like finishing the first like example. Okay. Anyway, like right now, like we already cover the model that is able to do like binary classification for us, right? But you may say like a lot of time we have like more than 2 classes, right? We have more than 2 classes. So how do we do? Okay, if you have more than 2 classes, what you can do is that, you can use softmax regression. In the softmax regression, the inverse link function is the softmax function. Okay, you replace the logistic function with a softmax function, which looks like this. So in other words, to obtain the output of the softmax function for the ith element of a vector, mu, okay, we take the exponential of the ith value divided by the sum of all the exponentiated value in the mu vector. So say, if your mu vector if your mu vector is like mu1, mu2, mu3, for example, and you apply this softmax, the result is going to be mu1, mu2, mu3, mu1. And the same denominator, mu2, and the same denominator, mu3. Okay? So you apply the softmax. It's going to be this one. It's going to be still like the n, entries. Okay. But now, okay, because all the terms have become like exponential, right? So think about this. Okay. No matter what your value of mu I is, all these terms are going to be positive, right? Because they become like e to the power of this some value, right? So all these terms will be positive. That's the first thing. The second thing is like, okay, every entry, this first one, the second one, the third one, okay, will be in the range of 0 to 1, right? Obviously, right? And the third thing that's also very important is that the sum of these three terms, if you add them up, is 1, right? Because they have the same denominator, right? You add them up, it happens to be the same as the denominator, which cancel each other to be 1, right? So that's why, okay, we use, this is an example that we can apply for like 3 classes, by the way. Okay, so the softmax, okay, is like the inverse link function that we use for like classifying like more than 2 classes. And by the way, to be honest, like if you consider 2 classes, the softmax will reduce automatically to be like a logistic function, by the way. You can try it yourself. Okay, so I'm not saying like softmax does not handle 2 classes, but if it's 2 classes, you just use a logistic function. Probably that's easily. Okay, that's easier. Okay, but if you use softmax for 2 classes, this thing automatically reduce to logistic function. Okay, and the regression that applies softmax is called softmax regression. Okay, so softmax guarantee that we will get positive values that sum up to 1, as I already explained. Okay, in a softmax function, it's reduced to logistic function when k equal to 2. I already explained all this. As a side note, the softmax function has the same form as the Boltzmann distribution used in statistical mechanics, okay, which is very powerful branch of physics dealing with the probabilistic description of atomic and molecular systems. But if you are not into these areas, you don't need to worry about that. Because remember, the author of the textbook is like his field is in the quantum chemistry. Remember, so he is more into this area. Okay, so he especially point out this. Okay, out of his own expertise. Okay, so Boltzmann distribution. Okay, and softmax. Okay, has a parameter called temperature T that divides mu when t equal to infinite, the probability distribution become flat and all states are equally likely. Okay, when t is close to 0, only the most probable state gets populated. And softmax behaves like a max function. But this is, you probably don't need to worry about that because this is just a side, just like a additional knowledge, atomic and molecular system, okay, in physics, okay. So the Boltzmann distribution, I mean, in Bayesian data analysis, we don't have to know that, okay. We only need to care about, what we only need to care about is the softmax, okay. So, yeah, so I think like, I'm running out of time because the next one is going to be a concrete example that use the softmax. You can imagine, okay, the example that we are going to use is still the Irish data set because Irish data set actually has 3 classes, right? Okay, so we could use it, okay, but I don't think we have enough time today. So we'll stop here today and continue on this multi-class classification, softmax regression topic. Not next week. Okay, remember next week I'll be out of town. Okay, so there's no class next week, but the week before, the week after next week, okay, we will continue the discussion here. Okay, so this is how many? We are. This is like 46. Okay, it's yeah, we still have like about 30 something slides. So next time we will finish this chapter and move on to the model comparison. But as I said, I'm not sure how much I can do, like because we have like only 2 lectures left. But anyway, okay, let's play it by ear. Okay, I will finish up the generalized linear model and then talk a little bit about model comparison next time, and then so the model comparison has like a little bit more than 1 lecture because I know like model comparison has like more than 100 slides, so obviously we cannot finish that chapter. So but anyway, yeah, just remember, okay, the homework 4 has been assigned, and the due date I believe is like it's a next Friday. Okay, next Friday. So you should have plenty of time. Okay, I believe like only one problem that we haven't covered. Okay, so next Wednesday we will cover the material that's useful for the last question that I assigned. All the other part of the homework 4, I mean, you should be able to do it now. Okay? So, any question? If no question, that's it for today, okay? So I'll see you in 2 weeks, okay? Okay, thank you, bye. Sorry for the delay, okay? It's some, I don't know why, but some other classes, I mean, tend to remove like the wire in the stand. I mean, so, but anyway, okay. I think we end up. Did we cover this slide and the next one, the Boltzmann distribution? Just want to make sure. So what was the last slide that we covered last time? Do you guys remember?
应该前几页吧。
前几页。这个吗？
再往前。好，应该是。
OK。
这一页。
Okay, okay. So, so this, okay. So, you can see that in this example, okay, we intended intended to make the classes unbalanced, okay, in the sense that where is it? Yeah, from here you can see that we only get like a 5, because we get rid of the first 45 entries from the Setosa class, okay, and but we keep the last one, okay, the Vescala, like all the entries in the Vescala. So the ratio for these two classes is 5 to 50, okay, 1 to 10, okay. So intentionally, pick this one, okay, like that, and then we pretty much feed that into the same model, okay. So the result figure, okay, is like this, and you can see the boundary, okay, is more leaning toward the minority class, okay, the minority class, which is indicated by the blue dots, okay. The blue dots are the Setosa, and the other one is the Vescala, okay. So so this is an example that show you what the unbalanced data is going to do to the data analysis, okay. So so what do we do, okay? If we find unbalanced data, I mean, the easiest solution is that if you are able to control the data collection, okay, if you are assuming you are able to control data collection, then you probably want to, get the data set with roughly the same number for each class, okay? I mean, so how do we consider, I mean, the classes, I mean, have roughly the same number? It doesn't have to be exactly 1-to-1 ratio, to be honest, okay? I mean, if you are into machine learning, okay, you will observe that, okay, yeah, of course, like the example that we observed, like, previously, like if the ratio is 1 to 10, okay, then obviously we have this unbalanced data problem, okay. But if the data set, for example, if you have two classes and the ratio is maybe 1 to 2, even 1 to 3, okay, I mean, if you just look at the number, yeah, I mean, they are not equal, of course. I mean, because, yeah, I mean, the minority class is still like a couple of times lower than the majority one. But if it's like 1 to 2 or 1 to 3, normally your analysis result will still be valid. Okay, so this unbalanced data, classes problem, okay, is not necessarily like happen that strictly, okay. It only happens when the minority class is like at least like one order lower than in terms of ratio, one order lower than the majority class. Okay, maybe 1 to 10 or even lower than that, then you normally have that issue. But if it's like 1 to 2, 1 to 3, okay, normally you do not need to worry about this impact too much. Okay, so of course this is the case. I mean, when you also deal with data collection. Okay, if you collect the data and you have control over like how many entries, how many examples you want to collect for each class, then this obviously is a good solution, right? Yeah, but unfortunately, okay, if you have no control over the data collection, okay, then you need to be careful when you interpret the result of this analysis, okay? So you have to check the uncertainty of the model and run some posterior predictive check, okay? So we have done that, I mean, many times, okay? But this becomes especially important when the data set is unbalanced because, yeah, I mean, the result may not be, correct because, as I said, like the boundary will, leaning toward the minority class. I mean, when this boundary is leaning too much toward the minority class, and it's not going to, I mean, give you a very, good analysis result. So, so another option will be to input more prior information, okay? Because obviously, like for this minority class, okay, I mean, you can try to provide certain prior information to fix this bias, But this is, it depends on how much you know about this data set, okay? Every time when we talk about like to provide like a stronger prior, it always involve like what kind of data. I mean, how much you know about this data. Okay, you cannot just provide an arbitrary strong prior and assume that will be okay. Okay, so this is like you can another way is you can run alternative model. Okay, I mean, I'm not sure if we are able to talk about that. I mean, because this is the model comparison chapter. Okay, today I'm trying to at least finish this chapter, and we still have like 1 week of class. So I'm going to, if I'm able to talk a little bit about the model comparison today, if I'm lucky, I probably can finish like less than half of that chapter. Yeah, that's the best I could do. Okay, but anyway, let's see what happens. Okay, and then the next topic is the softmax regression. Okay, what is softmax regression? The softmax regression, the function looks like this. Okay, softmax I mu. Okay, where mu is actually a vector. Okay, a vector with like maybe n components. Okay, n components. So you have mu1, mu2, mu3, okay, up to mu n. Okay, and so for each component, for each output component, okay, softmax I mu is going to be, you can see it's a summation of exponential of mu k. Okay, I mean, and the nominator is the exponential mu I. Okay, so first, okay, from this equation, you can tell that, okay, because that's like all the terms will be put into the power, right? So it's e to a power, where that power is a term of your input, right? Is so in that case, okay, you can imagine all this exp mu I, okay, no matter which mu I you are talking about, I mean mu1, mu2, mu3, up to mu n, okay, which mu I you are talking about, okay, exp to the power of mu I, it's going to be positive, right? Positive, I mean, it cannot be negative, right? Okay, it can never be negative. And the second, okay, you can imagine, okay, for each term, for each softmax I, okay,
obviously, okay, this result, okay, this result is going to be in the range of 0 and 1, right? Because the denominator is the sum of all the term, okay? So it's going to be exp mu 1 plus exp mu 2 plus exp mu 3 plus blah, 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 plus exp mu n. And then your nominator is one of those, right? So, it's going to be, the result is going to be in between 0 and 1, right? So this is the second thing. The third thing is what? The third thing you can observe is that, okay, the sum of all the terms, from this softmax, wow, how come this is? So the sum of softmax I mu, okay, I from 1 to n, okay, this is going to be 1, right? Right? Because the denominator are all the same, right? And numerator, when you add up all the numerator, it's going to be exactly the same as denominator, right? Right? So what does that remind you? What does that remind you? I mean, first, each item, each I, okay, each component of the softmax result, the range is between 0 and 1. Second, if you add up all these terms, okay, the result is going to be just 1. And each of them obviously is, it's positive, right? So doesn't that look just like a probability for you? It looks just like a probability, okay? And it is, okay? This softmax regression, okay, is used for, to classify n classes, okay? It's used to classify n classes. In the previous example, okay, the logistic regression, okay, we talk about binary classification, right? But now, okay, for this, okay, the softmax regression, we are actually talking about, we are going to use that for the multi-class classification. Okay, multi-class classification, okay? So, okay, softmax guarantee, we get positive value. That sum up to 1. Okay, that's obviously the case, okay? So then softmax function is reduced to logistic function when k is 2. When your n is 2, okay, the k here is the n I'm referring here. But when the total terms is 2, or the number of classes is 2, okay, obviously, okay, the softmax function should be reduced to logistic one, right? Because logistic function is used for binary classification, which means there are 2 classes, right? And the logistic function is going to output the probability of the positive class, right? And the other part obviously is 1 minus probability of positive class is probability of negative class. So which means like the logistic function also output the probability for 2 classes, pretty much, right? So conceptually they are exactly the same. You can check, you can verify this by yourself, okay? But I just want you to understand that softmax is softmax is an extension of logistic function, okay? In the sense that one is used for multi-class classification, one is used for binary classification. So, and as a side note, the softmax function has the same form as the Boltzmann distribution used in statistics mechanics. Okay, so this Boltzmann distribution is normally used for like in the physics. Okay, which is used to deal with probabilistic description of atomic and the molecular system, like this type of system. I mean, when they describe it, okay, they use Boltzmann distribution, but I mean, and there's like a parameter called temperature T, okay, that divides mu. Okay, when T goes to infinity, the probability distribution becomes flat. So all states are equally likely, and when T equal to 0, okay, approach 0, the most probable state, okay, will be 1, and the other states will become close to 0. Okay, it will become softmax will behave just like a max function. I mean, so this actually you just need to think about this a little bit, because really like in Bayesian data analysis, this is not that important. If you are into physics, obviously this is important for you. If you are because the author, okay, remember I told you, author is the guy who is into quantum chemistry, right? So he obviously has a very strong background in physics and chemistry. Okay, so that's why he was talking about this. But this is not that useful for if you are not into that field. Okay, so not only you need to replace the logistic with the softmax. Okay, if you want to do like a multi-class classification, you also need to replace the Bernoulli distribution with the categorical distribution. Okay, so the categorical distribution is the generalization of Bernoulli, okay, to more than 2 outcomes. Okay, and the Bernoulli distribution, okay, which represent a single flip, is a special case of binomial, okay, which represent n coin flips. So the categorical, okay, which represent a single row of die. Okay, I mean this is just an example because die has like the outcome of die has 6 outcomes, right, from 1 to 6. Okay, so it just represents like one multi-class classification result. Okay, so categorical is a special case of multinomial distribution. This multinomial distribution represents like n rows of a die. Okay, but right now, of course, I mean we only need to use the categorical. That's good enough. Okay, so so what do we what example do we use? I mean for this multi-class classification, obviously we can still use that iris data set. Okay, because iris data set in the previous examples, we only use 2 out of those 3 classes, right? Okay, but now, okay, with the ability to deal with multi-class classification, we could like consider the whole data set. Okay, now, okay, so you can see that we use all the 3 classes: Setosa, Vesicular, and Virginica. Okay, and also, I mean, we try to make use of all the features. There are 4 features. Okay, sepal length, sepal width, parallel length, parallel width. I mean, we talked about this, I mean, previously already, right? So we are also going to standardize the data. I mean, so that's represented in the last line. Okay, so each data, okay, we subtract the mean of that, and also we divide the standard deviation. So we normalize like each feature. Okay, but okay, we could have also just centered the data. We don't have to normalize the data. I mean, for like a better result, okay, we need to at least center the data. Okay, so this also gives you an idea. Like remember, like when you need to deal with that the term project, you could try like standardize the data, or you can consider I mean, at least center the data, okay? So anyway, okay, so once we have done that, okay, we will create a model for that multi-class classification, and you can see that this is actually a very simple one, okay? So the alpha, beta, okay, they pretty much like similar to what we have done previously, okay? And the mu, okay, is the alpha plus like, you know, your max multiplication result, xs and beta, okay? Remember, this xs and the beta are both like in matrix form, okay, in the matrix form. So you can see it's a 4-3. Shape is 4-3, okay? It's 4-3 because we have 3 classes and we have 4 features, okay, by the way. And then, okay, you know, we have this theta equal to tt dot nnet dot softmax. This tt just like it's an abbreviation of Steno, okay, Steno dot tensor prefix, okay, Steno dot tensor prefix. So we just abbreviate it as tt, okay. And I mean this statement actually calls the softmax function, which is provided, I mean, under the Steno dot tensor package, okay. So we apply the softmax, okay, on this mu. Remember, this mu is a vector with 3 components, okay, because this is 3 classes. So once you apply that, we get like a probability for those 3 classes, and then you know we feed that into categorical, okay, and we put p equal to theta observed equal to ys, and you know, and we try to generate like samples, 2,000 samples. Okay, so that's it. Okay, so if you try it out and run the code, okay, you will find that, okay, yeah, this is like you can try to see like the result of this model on the data set, and this is a piece of code, and then the result is that, you know, the data set is, I mean, this model is able to classify 98% of the data set correctly. Okay, obviously, I mean, this is very good. Okay, only 3 entries are, you know, are misclassified. Okay, so I mean, but is it that good? Is there like any problem with that? Obviously, okay. Here, okay, what we try to do is that we actually try to use the training data set to verify the effectiveness, the correctness of the model. But keep in mind, the model is trained by the training data set. So obviously, if you use the training data set to verify the model performance, obviously it's going to give you a much better one. Okay, so normally, okay, what happens is that what we want is like you want to reserve like a portion of the data, okay, for the as a test data set, okay, and use that to evaluate the model performance. Okay, you don't want to, you know, use the training data set to verify the model performance, because obviously there's a bias. Okay, I mean, the model is already trained on this data set. I mean, so it obviously should perform, I mean, much better. Okay, on this data set. So this is like you know, actually it gives us the overestimate. We overestimate the ability of the model. Okay, so we don't want to do that. So that's why I say like we want to divide the data set into training data set. Sometimes we even want to divide it into training, validation, and the test data set. So, so the takeaway here is don't use the training data set to evaluate the model performance. Okay, otherwise you are going to overestimate the performance of your model. Okay, so anyway, one more thing to talk about is that, okay, you can run the posterior predictive check and you can run the summary of this result. And you will find that the marginal distribution of each parameter, okay, are very wide. The posterior are very wide. Okay, the 96%, right? Posterior, the PD, okay, is going to be very wide, okay, for different parameters, okay. So they are as wide as, indicated by the priors, okay. So how come it doesn't, shrink the distribution, after we incorporate the data, okay. So there's some problem, right? I mean, but make no mistake, okay, the model performance, even though we overestimate it, okay, but, by using the same training data for estimation, but the model performs okay. But the problem is like the posterior of your parameters, okay, doesn't look right? So, so even when we were able to make correct predictions out of the model, okay, so this does not look okay, okay. What happens? Okay, so this is the same non-identifiability problem that we already encountered for correlated data, okay, in the regression model. Remember, if you have two variables that are very, very highly correlated, okay, you will find that it is difficult to control the posterior of those like highly correlated parameters, right? Okay, that's pretty much the same issue here, okay? Okay, in this case, the Y posterior is due to the condition that all probabilities must sum to 1. This is obviously the case, okay? But this one, okay, look at this model. Okay, even though this model, okay, is a correct one, it's a perfect, fine model, but the issue is that this model does not include that restriction here, right? Because all the probability has to, sum up to 1. Obviously, this is one more restriction, right? It's a one more restriction that is not considered in the model construction. Okay, so what do we do? Okay, given this condition, we are using more parameters. Then we need to fully specify the model. Okay, so it's kind of like you have more condition than the number of parameters, number of variables in the model. So in simple terms, if you have 10 numbers that sum to 1, if you have 10 numbers, if we know like there are 10 numbers, they will be summed to 1. You just need to give me 9 of them, right? Because the other one we can calculate to get it, right? Okay, same here. Okay, same here. One solution is to fix the extra parameters to some value. So we intentionally fix an extra parameters, one extra parameter to some value. Okay, for example, to fix that to 0, and so that this problem can go away. So this is the improved multi-class classification model, okay, over the previous one, obviously, okay. So the first two terms, I mean, the only one you can see, I mean, the second one you can see that this is, the shape is no longer 4-3, it's 4-2. So in the sense that we only output the probability of two classes, because the third one we can compute. That's exactly what we are talking about here. And then, okay, so the third one, okay, see, we intentionally concate a 0 to alpha, and the concate like, we use NumPy zeros to generate like some number of zeros, and concate that to the matrix. Okay, and then, okay, the other part will be exactly the same. Okay, so we intentionally put like a one class, okay, to be 0. And the result is actually better than the previous one, okay? It should give us the same model in the sense of the performance. The model performs the same, I mean, exactly as good. But now, I mean, if you look at like the distribution of the posterior for like different parameters, they will look much better. Okay. So so far, okay, we have discussed the logistic regression and a few extensions, okay, such as like softmax, okay, regression, okay. Oh, by the way, the previous example, this is called softmax regression, okay. If you use softmax as like to replace logistic, that's normally how we call it, okay. So in all cases, we try to direct compute the P of Y given the condition of X, okay. So that's the probability of a given class not knowing X, okay, with X being the features, or you can say the X being the data, okay. So we measured two members of the classes, okay. So in other words, we try to directly model the mapping from the independent variables to the dependent variables, okay. So we try to find this mapping directly, and then use a threshold to turn the continuous. Remember, the result we are getting, okay, it's going to be a probability distribution, right? Okay, you are going to get a probability for different classes, okay? And the probability obviously is a continuous result, right? We are going to turn, and then we use like the boundary to cut like the continuous result into discrete boundaries, okay? So the boundary is used to divide the continuous result into discrete classes, right? That's how we did it, okay? That's how we did it. That is what, well, even this one, see, this is like this boundary that we generated is used to divide the continuous result into like a discrete one. And the one that is even more obvious is this this one. Yeah, this is a boundary, right? I mean, obviously the result is a continuous result, but we use a boundary to determine like okay, to break it into two classes, right? So this is always, I mean, the case, okay, for the logistic regression or softmax regression, okay. But, okay, so this approach is not unique. There are other approaches out there. Okay, what is the other approach? Okay, one alternative is to first model P of X on condition of Y. Okay, this is the distribution of X for each class. Okay, and then assign the classes. Okay, so this one, okay, we try to get Py on condition of x. But this one, okay, we first model P of x on condition of y. Okay, so that's exactly the opposite. Okay, so this kind of model is called a generative classifier. Okay, I mean, I know like recently the generative model is popular in AI. Okay, for example, like the ChatGPT is I mean one of the most well-known generative models. Okay, but this in this in the Bayesian data analysis, we also have this type of generative classifier. Okay, this generative classifier, we are able to create, we can generate samples from each classes. Okay, so the previous approach, the regression model, okay, regression-based model is not able to generate sample for each class. Okay, but this generative classifier is able to do that. So this is one big advantage over the regression models. Okay, such as logistic regression or softmax regression. Okay, so on the other hand, logistic regression is a type of discriminative classifier. Okay, so it's a discriminative classifier because it tries to classify by discriminating classes. Okay, so we are trying to create classes from the continuous space. So that in mathematical term, we call that we are discriminative classifier. We call that discriminative classifier. So, but we cannot generate examples from each class from the model. Okay, so this is the drawback of that. But obviously, it can be used to classify for the classified purpose. I mean, very well. Okay, so we are not going to go into much detail here about generating models. Okay, for classification, but we are going to see one example that illustrates the core of this type of model for classification. So we are going to show you one example of this generative classifier. Okay, so we are going to do it for two classes and only one feature to make our case simple. Okay, I mean we restrict the problem into just two classes and then one feature here. Okay, so just like the first model we built, I mean in this chapter. Okay, remember like the first model the first logistic regression model we built for this chapter is we consider two classes and one feature. Okay, that's like the S shape and the boundary that we are getting. Okay, I mean that one. Okay, so we are going to use exactly the same class, same data set. Okay, two classes, one feature. Okay, so we so far as PyMC3 implementation of generative classifier. Okay, yeah. Let's take 10 minutes break. When we come back, let's talk about this this model. Okay, let's take 10 minutes break first. Okay, is it good? Okay. Okay. So, okay, so this is an example of such a generative classifier. Okay, so this is called linear discriminant analysis. Linear discriminant analysis model. Okay, but you can see even though we have a term discriminant here, but this LDA model is generative. Okay, I mean because we just say like the regression models are the discriminating doing discriminating to classify classes, but this is called linear discriminant analysis. So just don't be misled by the name. Okay, so you can see that here. Okay, mu. Okay, we have a prior. Sigma, we have another prior, and you can see we directly have like a setosa. Okay, equal to PM dot normal. We assume, okay, this class is in Gaussian distribution or normal distribution. Okay, and the name setosa. Mu is from mu 0. Okay, remember, I mean here, for both mu and the sigma, we have like a shape. I mean, we have more than one. Okay. Sorry. Okay. So mu is mu 0. Standard deviation is sigma, and observed. Okay, we directly get the data. Okay, to fit here, and Vescala, same thing. Okay. Mu is another one, mu 1, and then we directly get the data to fit with that. So once we have that, okay, obviously we are able to, what should I say, have the result for mu 0 and the mu 1, right, based on the data. And then the interesting thing for the LDA is that the boundary is actually a closed form. It can be directly computed from the mu 0 and the mu 1. Okay, basically just, okay, we call the boundary, okay, as a BD, and then, the boundary is assigned to be the average of mu 0 and mu 1. And then we generate 1,000 sample. Okay, so this is, different from the previous model in the sense that, you see, in all the model that we have seen normally, you can see we normally feed the data. For example, observe equal to ys. We feed the data. Into the result model for the last line. But here, okay, in this example, for the generative model classifier, you can see that, okay, the place we fit the model, with the data set is here. This one and this one. And then after that, we compute the boundary. Okay, so this is very, very different. Okay, very, very different. Okay, and you can also plot the figure, okay, to show these two classes. Okay, this is the important. We can still get 94% HPD, okay, out of it, okay, and it looks like this. And if you compare this one with the one we had for the regression, logistic regression model, okay, it's going to take some time to this one. You will see that the result is pretty much identical, almost. Okay, use regression, logistic regression, you get the boundary like this. If you use like LDA, obviously the idea is different, but you still get pretty much the same boundary. Okay, and you can also output the summary of this so that you can compare it with the boundary that you have in the previous logistic regression model result. Okay, you will see they are almost identical. Okay, almost identical, pretty similar. Okay. So this LDA works for the two classes and one feature. So it's a very limited application. It has very limited application. Because if you want to extend this model to maybe more than one feature, okay, you want to model or you want to model by classes as multivariate Gaussians. Okay, so this is going to be obviously more features, more than one features. Okay, then it is possible to relax the assumption of the classes sharing the common variable covariance. Okay, I mean in this LDA, if you look at the code that we were writing. Okay, here. Okay, sorry, where is it? This one. Okay, yeah, we have different mu. Okay, but these two setosa of this color share the same sigma. Okay, this is obviously one assumption that we have for the LDA. Okay, but if you want to relax this assumption, okay, such that each class has its own variance, okay, this leads to a model known as quadratic linear discriminant, QLD. QDA. Okay, so now the decision boundary is not linear but quadratic, so it's more complicated. Okay, and in general, LDA and the QDA model will work better than logistic regression when the features we are using are more or less Gaussian distributed. So if you already know, okay, this is the problem, okay, where your features are Gaussian distributed, then you probably prefer to use LDA or QDA because they will tend to give you a better result, okay? But if if you cannot be sure about the distribution of your feature, okay, then the logistic regression will perform better in the other cases. Okay, so basically it depends on the problem. Okay, which type of problem is more suitable for LDA, QDA, this type of generative classifier? Which type of problem is good for a regression type of solution? Okay, here is a very important hint for you. Okay, and one advantage of a generative model for classification is that it may be easier or more natural to incorporate prior information. Okay, so we may have information about the mean and the variance of the data to incorporate into the model. And obviously, because here, okay, when you write the model, okay, it's easier for you to incorporate different priors, okay, to different classes. Okay, so that's one advantage of that. Okay, but to be honest, the regression type of model can do that too, but it's just not as straightforward as generative classifier. Okay, so it is important to know that the boundary decisions for LDA and QDA are known in closed form, and hence they are usually computed in such a way. So, for example, LDA is just the mean is just of the boundary is just the average of the mean, right? And for QDA, yeah, it's more complicated, but you can still use a quadratic form to calculate the boundary. Okay, so to use LDA for two classes and one feature, we just need to compute the mean of each distribution, average those two values, and that's it. So in the preceding model, we just did that, and with a Bayesian twist, because we are actually doing the calculation from the distribution, so we are able to also get for example 94% PDA, okay, HPD. I'm sorry, HPD. Okay, so that's very nice. Okay, so we estimate the parameters of the two Gaussian, and then we plug those estimates into a predefined formula. So where do the formula come from? Without getting into too much detail, to obtain that formula, we must assign the data is assumed, we need to assume the data is Gaussian distributed. And hence such a formula will only work if the data does not deviate from normality too much. Okay, so this is an assumption that we have. I mean, that the data, the features are Gaussian distributed. Okay, I mean, if it's not the case, I mean, it's much more complicated. Okay, of course, we may hit a problem if we want to relax the normality assumption. Okay, can we do that? We could. Okay, such as using student t distribution if you have a lot of outliers, and you want to deal with those outliers. Remember, the way to deal with outlier is to, instead of using Gaussian, we can use student t, okay, or multivariate student t distribution. I mean, in the case if you have like multiple variables, okay, then, okay, in such a case, we can no longer use the closed form for the LDA. I mean, the result of the boundary is no longer a simple computation. Okay, it's not a closed form. Okay, or QDA. Okay. However, we can still compute a decision boundary numerically using PyMC3. Okay, but we will stop our discussion here. Okay, if you are interested in like a generative model, generative classifier, I mean, you probably want to check out the references that I have provided at the beginning of this class. Okay, there are more discussion on this type of stuff. Okay, so now, okay, the last topic, okay, for this chapter is like sometimes we want to predict or like to calculate or to inference, okay, a certain number, okay, which is the count data type. Okay, the count, I mean, data type is like first it must be integer, right? If you count something, I mean, it must start from 0, right? I mean, well, I mean, the worst case is you don't count any event, then that's E0. You couldn't get a negative number, right? So this is like how do we deal with such a prediction? Okay, using the linear model. Okay, is we can use a Poisson distribution. We call such a regression Poisson regression. Okay, so this model assumes data is distributed according to Poisson distribution. Okay, so one scenario where Poisson distribution is useful is when counting things. For example, the decay of radiative nucleus. Again, this author, I have to keep reminding you the author's background because he's into like the quantum chemistry. So the example he used is not so what should I say? Not so straightforward for regular people. Okay, so this because you probably don't know the decay of a radiative nucleus is countable, right? At least I don't know that much. Okay, but the other example, okay, I think is much more friendly. Okay, for example, the number of children per couple. You can have some. I mean, your significant other can have some children. Okay, but the number of children can only be integer, and it can only be 0, 1, 2, 3, right? Obviously, okay. Or the number of Twitter followers. Okay, again, that's a simple example for the count data set. Okay, so what all these examples have in common is that we usually model them using discrete non-negative numbers, such as 0, 1, 2, 3, blah, blah, blah. So this type of variable receives the name of count data. So the previous example, for example, like regression, okay, linear regression or multiple linear regression, deal with like predicting a value, right? That value does not have to be integer, right? Okay, for logistic regression, we are predicting or classify. We are classifying like a binary class, right? For softmax regression, we are classifying multiple multiple class classification. Okay, and but this one, the Poisson regression, deal with like we are predicting the count data type. Okay, that's important. So for the Poisson distribution, imagine we are counting the number of red cars passing through an avenue per hour. We only count the number of red cars, not the other color, just the red cars. Okay, so we could use Poisson distribution to describe this data. Okay, so what is the nature of Poisson distribution? Poisson distribution is generally used to describe the probability of a given number of events occurring on a fixed time or fixed space interval. Okay, for a given time or given space interval. Okay, if you want to describe the number of events, okay, that will occur, okay, within this fixed interval, then we normally use Poisson distribution. Okay, so the Poisson distribution assumes that events occur independently of each other and at a fixed interval of time, okay, or space. So again, this independent assumption, okay, is an important one in the Poisson distribution, and luckily in most of the applications, we could assume such a assumption. Okay, the event happen independently. Okay, but this is not necessarily the case. Okay, sometimes one event will impact the occurring of the next one. Okay, this is like sometimes this assumption doesn't work. Okay, but most of the time it works well. Okay, so this discrete distribution is parameterized using only one value. Okay, which is a rate. Okay, which is normally use the lambda to represent that rate. Okay, so mu corresponds to the mean and also the variance of the distribution. So the probability mass function of Poisson distribution is given like this. And you may wonder what is the relationship between the lambda and the mu, because lambda is rate, right? And the mu is the average. Okay, so rate is normally, okay, lambda is normally 1 over mu. Okay, and but in this formula we only use mu here. Okay, and also one important thing you need to remember is that, okay, Poisson distribution is only the few distribution that the mean and the variance are the same. Okay, mean and variance are the same. Okay, both of them are represented by mu, by the way. Okay, so here mu is the average number of events per unit of time space. Okay, x is a positive integer value. Okay, so here x is that refer to that count data. Okay, x, a factorial of x, you know the factorial, so I don't need to explain. Okay, so this small piece of code will plot the Poisson distribution family for different value of mu for you. Okay, here I want to remind you, I would like to remind you that Poisson distribution is not a continuous distribution. The reason we draw this looks like a continuous distribution is just to give you an idea, okay, how this distribution change over different like interval. But I mean in reality, I mean where this distribution really take value is that integer value. So you can see, I mean, those values were like marked by the big dot. Okay, I mean the line between the big dot is just an indication of the trend, but it doesn't. It's not the indication of that. Oh, there are values in this interval. No, because Poisson distribution is a discrete distribution. Okay. So, you can also see that, okay, because mu indicate like the average number of events for a given period of time, right? So the more, the higher the mu, okay, you know, the more likely, okay, for example, mu is, when mu is 8, okay, you can see the distribution looks like this. You have more chance to have a higher count value. And when the mu is very small, such as mu is 1.5 or mu is 0.5, you can see that, okay, the chance for mu to have like a high value is, I mean, it decreased drastically, okay, drastically. I mean, after, I mean, you know, a few counts, okay, and also. Just want you to remember that even though I say, you know, the Poisson distribution is a discrete distribution, right? The value of mu does not need to be integer because mu is the average number of events for a given, you know, time interval, for example, and that average may not be integer. So just like what you see here, it could be 0.5, it could be 1.5. That's fine. That's fine. That's a valid value for Poisson distribution. Okay. So mu can be float. Okay. So so remember, Poisson distribution is a discrete distribution. Okay. The Poisson distribution can be seen as a special case of the binomial distribution when the number of trials n is very large, but the probability of success p is very low. Okay, so without going into too much mathematical detail, we can try to clarify this statement. Okay, so following the car example, we can affirm that either we either see the red car or we do not. So we can use a binomial distribution like this. This is a probability that we see a red car. Okay. So, I mean, in this case, the mean of the binomial distribution is like, you know, this is very simple calculation, like it's n times p. And the variance, okay, you can, again, this is a simple calculus. It's going to be np times 1 minus p. But if, I mean, even if you are in very busy avenue, okay, the chance of seeing a red car compared to the total number of cars in a city is very small, right? I mean, for example, in Taiwan, I mean, for some reason, this is, by the way, a very interesting observation. I mean, if you go to a street and try to see like a different car in different colors, you will find that the cars in white, I mean, you have most of the car in white. I don't know why. Okay, I don't know why. Because I just came back from US. Yeah, I wouldn't say. I would say like the variation in color for cars in US is much more than the variation of the cars in color in Taiwan. Okay, I don't know why. But in Taiwan, I mean, the number one color in cars is white, and the second highest one is probably black, right? I don't know. I don't know why. I mean, everybody, but my car is also white color. Okay, I'm not saying like there's any problem with that. I mean, even for myself, I use white color. I mean, the reason I got a white car is because like the sales tell me, car sales told me like the white color, it's easy to see if there's any if there's a dirt on the car, it's easy to see and you can easily wipe it out. But well, you will find that, I mean, that's the majority of the color on the street. Okay, but anyway, okay. So obviously the chance of seeing a red car compared to the total number of cars in a city is very small. So in other words, okay, the N is much larger than P. Okay, number of cars is much larger than P. Okay, so in other words, N times P, okay, is roughly the same as NP times 1 minus P, right? Okay, I mean statistically speaking, or like numerically speaking, NP and NP times 1 minus P, I mean, they are very close. They are very close. The only difference is the factor 1 minus P. But since the P is small, so these two terms are similar. So if that's the case, so you can see you can approximate the variance by NP if the average and or mean, okay, if the mean or like expected value and the variance are both NP, then we can confidently state that our variable is distributed as a Poisson distribution. Okay, so that's why we normally consider Poisson distribution as a extension, okay, or like a special case of like a binomial distribution. Okay. So obviously we could use like a Poisson distribution to deal with like the number of car prediction, okay, on the street. Okay, so you can directly do that. Okay, but sometimes, I mean, if you do that directly, you will find that, okay, the predicted number is usually, okay, always smaller than the real value. Okay, so what should I say? It's the opposite. The predicted value is usually higher than the real value. Let me correct myself. Okay, so you have fewer zeros compared with the data. Okay, this is almost always the case when it comes to the Poisson regression. So what do we do? I mean, of course, like we haven't. I mean, we didn't see an exact example here. So I encourage you guys to really like create a simple Poisson regression and compare that with a count data set, and you will see like this phenomenon, which should convince you, okay, to explore ways to correct that. Okay, so what do we do? Okay, so first, I mean, let's consider what happens. I mean, why do we have that? Okay, so when counting things, one option is to not count the data a thing. That is to get a zero. Okay, so number zero can generally occur for many reasons. Okay, so we get a zero because we were counting red cars. Okay, that and a red car did not pass through the avenue. Okay, so there's no red car. Okay, or because we missed it. Okay, either there's no red car or we missed it. Okay, what do we mean by we missed it? Okay, maybe we did not see that tiny red car behind a large truck. Okay, the car can be blocked. Some cars can be blocked by the other cars, right? So sometimes, I mean, when you count the red cars, I mean, you miscount some events. Okay, that happens like from time to time anyway. So if we use a Poisson distribution, we will notice, for example, when performing a posterior predictive check, that the model generates fewer zeros compared to the data. So when it generates fewer zeros compared to the data, it means we have too many ones. Okay, the number one is a little bit too high, too high. So how do we fix that? That's here. I mean, I just want you guys to understand the reason, the phenomenon, the issue. Okay, where the problem comes from. Okay, so we may try to address the exact cause of our model predicting fewer zeros than observed one. Okay, and include that factor in the model. So we can fix that, okay, directly. Okay, for example, we can incorporate like a stronger plier, okay, to fix that. That's obviously doable. Okay, that's obviously doable. But I mean, you probably need to know. For example, you miss the events, right? So what is the rate that you miss the events? Okay, you need to know a little bit better about that to design a more reasonable plier, okay, in order to incorporate that into your model, okay. But you know, this is not very convenient, okay. As is often the case, it is enough and easier for our purpose just to assume that we have a mixture of two processes. This is like one solution that is much easier, but this solution, okay, require you to mix two processes, okay. One modeled by a Poisson distribution with probability psi, okay. I mean, so this part, the first part, is the simple Poisson regression that I was talking about. Okay, so this part is just like what it is, like you know, when you use a Poisson distribution to replace the logistic or like softmax. Okay, so that's easy. I mean, so with the probability psi, okay, you model, you put the part to be modeled by Poisson distribution. The other part, when given extra zeros with probability 1 minus psi, okay, and obviously psi and 1 minus psi, I mean, they add up to be 1, right? So you consider all the cases. So you can sort of consider this second process as the process that you miscalculate a car, the red car. You miscalculate a red car. Okay, some red car that, you know, either got blocked by the other cars or you simply just missed it. Okay, and the second process deal with that. Okay, so how do we call such a model? We call it zero inflated Poisson model. Zero inflated Poisson model, and which has a very nice abbreviation called ZIP. Okay, ZIP, zero inflated Poisson model. Okay. So in some text, you will find that psi represent the extra zeros, and 1 minus psi the probability of the Poisson. I mean, basically, it's the opposite, exactly opposite. Okay, but it doesn't matter. I mean, it's really like the choice of the programmer to do the model. Okay, so you know, this is not a big deal, obviously. I mean, just pay attention which is which for a concrete example. Okay, So basically, a zip distribution is like this. Okay, so when the outcome is 0, okay, we have 1 minus psi plus, okay, because here, okay, remember maybe it's easier for us to look at this one, okay? When the outcome is not 0, okay, this is what we get, right? This is Poisson distribution function, I mean, obviously, right? No problem with that, right? Okay, so when outcome is 0, okay, I mean, for 1 minus psi, I mean, you have this missed calculation, okay? And then the other part, okay, it's going to be, you know, this probability. Why is this probability? It is, you know, when the outcome, I mean, the outcome is non-zero, okay, but, you know, you, how should I say? I shouldn't say outcome is non-zero. The other part, okay, when you have something that you follow the Poisson distribution, and you plug in x to be 0. When you plug in x to be 0, this part becomes 1, right? When you plug in x to be 0, the factorial of 0 is 1, right? So they will leave just e to the power of minus mu, right? So that's this part is what came from the Poisson distribution when you have a 0 event. Okay, so but you add this 1 minus psi, okay, extra probability to it to sort of adjust that. Okay, sort of adjust that. So here, okay, 1 minus psi is the probability of extra 0. Okay, and then let's try an example. Okay, we create a few synthetic data points. Okay, so we have 100 point. Okay, the real theta is 2.5. Okay, and the psi is 0.1, and then we just randomly create some numbers, and then so the numbers looks like, well, it doesn't give you those numbers, but anyway, so this model is very simple. Okay, I mean, okay, we call it just zip. Okay, psi is like from a beta distribution with alpha and beta, A and B to be both 1. Okay, when A and B are both 1, remember it's a flat, right? If you remember the beta distribution, when A and B are both 1, I mean, it's a flat. So it's this one is a non-committal prior for psi. Okay, we just know like a psi is a value between 0 and 1, and then okay, theta, okay, is going to be, I mean, PM dot gamma, okay, we just call gamma, okay, theta 2, 0.1, okay. Here, I mean, we, this is like a prior, okay, this is a prior to that theta, okay. And the 2 and 0.1 is not a very strong one, okay, strong prior. But then, okay, what happens that, okay, after you have the theta, 2 and 0.1 is a prior, right? And after you have that theta, you put theta here, and we call the zero inflated Poisson. So this zero inflated Poisson already have the function like this, okay? But you need to provide like a adequate like parameters, okay? So you put the psi from here, you put theta from here, okay? Where theta has to be in a gamma distribution. Okay, sorry, gamma is a prior. Okay, gamma is a prior. Okay, so theta is just. I mean, by the way, this gamma is a very flat gamma. Okay, flat result. So I mean, you just provide the theta here, and observe data. Okay, and then you just do this generate a sample. That's it. Okay, and then this is a result. Okay, of like trace file, trace result. Okay, and then okay, so it actually gives us like a pretty nice result. Okay, because you can see here. Okay, theta. Okay, because the real theta is 2.5, right? Real theta is 2.5. Real theta is 0.1. So you can see like the highest place for psi is, you know, in between 0.1 and 0.15. Okay, somewhere here, in the middle of maybe 0.12 or something like that. Okay, and for the theta, you can see, okay, it's going to be, again, it's in between 2.5 and 3.3. So it's close enough, okay? It's a close enough, estimate for the data set, okay? So just want you to understand, okay, this example, okay? So then, the zip model may look a little dull, but sometimes we need to estimate simple distribution, such as the one that we just used, okay, the example we just used, or others such as Poisson or Gaussian distribution. So anyway, we can also use Poisson or zip distributions as part of linear model. So as we saw in the logistic and softmax regressions, we can use an inverse link function to transform the result of the linear model into a variable in a range suitable to be used with other distributions than the normal. Okay, so follow the same idea, we can now perform a regression analysis where the output variable is a count variable using a Poisson or zip distribution. So this time we can use the exponential function e. Okay, the reason to use e is to, you know, to make sure it's bigger than 0. Okay, the result is larger than 0. Okay, as the inverse link function. So this, if you want to use a count, deal with count value, the inverse link function is usually e. Okay, exponential. Okay, so this choice guarantees the value returned by the linear model are always positive. That's what I said. Okay, so you can see that, okay, alpha plus x beta is the power term for the e. Okay, and you assign this one to the theta, and then you do whatever you want for the theta. For example, you apply the Poisson or zip on the theta, maybe. Okay. So here, okay, is another example we can use. Okay, this is a data set from the Institute for Digital Research and Education. By the way, do we have anyone here from maybe Professor Chen's lab, Chen Guodong's lab? No, not here. Or Professor Yang Zhenhua's lab? No? Okay. Because they are doing some research on education. So maybe this example is an interesting one for them. Okay. Unfortunately, we don't have anyone here in their lab. But anyway, so to exemplify a zip regression model implementation, we are going to use to work with a data set, okay, from this Institute for Digital Research and Education. Okay, so we have 250 groups of visitors to a park. So this is 250 groups of visitors, to a park. This is not exactly about the education, but this is the data set collected by a research and the education institute. Okay, so here are some parts of the data per group. Okay, this is the following describe like either feature or the count data. Okay, so I mean first the number of fish they caught. Okay, obviously there are fish. Okay, in the river in this park. Okay, some park do not have a river. Okay, but in this case, I mean it must have some. That park must have some river. Okay, so the number of fish this group caught. Okay, and by the way, I mean you may ask how do we calculate? I mean obtain such a value? But because in U.S. okay. This thing must be collected in U.S. because like in U.S. like you can buy license to catch fish, and the license allows you to collect a certain to catch a certain number of fish per year. So how many? No, you basically need to report like how many fish you catch. Okay, every time you go fishing. Okay, because you don't want your fish license to exceed your limit. If you do that, I mean, you'll be fined like terribly. Okay, so this is I mean why I mean in U.S. like everyone okay if they go fishing they will report the number of fish they caught. Okay, so they have this information number of fish they caught, and how many children were in the group. Okay, and whether they brought a camper to the park. The camper is not popular in Taiwan. Okay, camper is kind of like the type of car that you can live in the car. Okay, you can stay in the car for overnight. Okay, and obviously, I mean, for every camper, I mean, there's like a kitchen that allows you to. Maybe you can once you catch a fish, you can process it and cook it as a dinner. Okay, for everyone. Okay, so it's nice to have a camper. By the way, but obviously it's also I mean it's considered expensive. Okay, but in U.S. like if you buy a camper, obviously you can just park in your garage. But in Taiwan, I think like. Maybe the price of camper is not that expensive compared with the price to park it. Okay, I mean in Taiwan it's just crazy to park the car. Okay, anyway, okay. So using this data, we are going to build a model that predict the number of caught fish as a function of child and the camper variables. Okay, so we are going to use the second one and the third one as features to predict the first one. Okay, so we can use pandas to load the data. So fish data, okay, we just read CSV, okay. So this data set is called fish.csv, okay, which is provided by the book, okay. So you can explore data set using plots or pandas function, okay, such as, yeah, well, I think it's let's take 10 minutes break. When we come back, we will continue our discussion here, okay? Hopefully we'll finish this example and also this chapter next hour, and then talk a little bit about the model comparison chapter, okay? Okay. So, so you can see that increasing complexity, okay, is going to increase the accuracy. Okay, of course, I mean, this accuracy is calculated based on the training data set. Okay, it's based on training data set only. Okay, so so we know that, okay, this is like there's a trade-off between the complexity and the accuracy. Okay, so the polynomial of order 5 able to capture the data without missing a single data point, because we have only 6 data points in this particular example. So obviously, the model of order 5 has 6 unknowns, which is enough for us to capture these 6 data points without any problem. Okay, I mean we learned that from the high school math. Okay, so but this really just memorizing stuff. Okay, because when you create a model, what you want to capture from the data set is the trend, not just memorizing the data, in the data set. Okay, no. What we want to explore is the trend in the data set. So, for example, you see this 6 point, 1, 2, 3, 4, 5, 6. You can see that, most likely the future data will appear somewhere along this line. Okay, I mean, this is the trend. Okay, this is shown in the trend. Okay, I mean as a trend. So, but obviously, if you use this model of order 5, you can obviously see that after this point, this model will jump very high, right? And after this, before this point, this model is going to go down very deep as well. So most likely, this model of order 5 does not capture the trend of these data points. Although, if you evaluate the accuracy of a model by the training data set, this model gives you the most accurate one. But this is normally not what we really want. So imagine if we get more money or time and we are able to collect more data points. Say we are able to collect 2 additional points, 10, 9, 7, 7. So these 10, 9, 7, 7 are represented by these 2 squares here. Which, by the way, fits our intuition, right? Because these 2 points appear close to this direction, right? So it is reasonable additional data point to add. But if you look at the arrow of these 2 data points, you will find that the arrow from the linear model is much smaller than the arrow. For the model is order 5, right? So this is like the model. The order 5 model does a very poor job at generalizing to future unobserved but potentially observable data. Or put it another way, when you use this model for prediction, because when you do the prediction, you are supposed to use like something that will happen in the future, to fit to your data, your model, right? So obviously that future data will not appear in your training data. So no matter how accurate your training data show you, the accuracy of the training data does not, is not an indication of accuracy for the future data. So for the future data or for the test data, I mean, if you allow me to use like machine learning jargon, then it will the accuracy and the complexity of model will look like this, actually. So, so overfitting is a general problem where a model fits very well with the data set that was used to learn its parameters in the first place. So this is the training data, So, but it's very bad at fitting other data set we say that we have overfitting. This phenomenon, okay, that the model perform well in the training data set. I mean, when I say perform well, I mean the error is small in the training data, but is large in the test data or in the future unobserved data. We call such a phenomenon as overfitting. So this is a very general problem in statistics and machine learning. So a very useful way to picture the problem of overfitting is by thinking that data sets have two components. There are two components in the data set, the signal and the noise. Okay, the signal, okay, aka the trend, okay, I previously used the term trend. That actually just represent the signal. Okay, this part, the signal is, or the trend is what we want to capture by the model. Okay, so the future data or test data, whatever we call that, okay, will obviously, follow this signal or follow the trend. Okay, so it is very important that your model capture this signal, okay, or the trend. Okay, but the noise is what you have. Okay, when you are doing data collection or when there's more function for the sensors, or the limitation of the measurement tool. Okay, a lot of this will contribute to those errors. Okay, so those errors, okay, the errors are the one that we want to ignore. Okay, we want to ignore from the data set, but because the data set contain these two components together, it's very difficult for you to tell which part is the signal, which part is the noise. Okay? So a model overfits when it is so flexible that it learns not only the signal but also the noise. Okay? So it learns the noise too well, and it will hide the signal. Even though normally it also learn the signal, but because the noise, okay, it actually hide the signal. Okay, this is a practical justification for Occam's razor. Okay, that's why we prefer simpler model. Okay, remember Occam's razor suggests us to take a simple model, right? So this is a justification for that. Okay, so in principle we can always create a model so complex that it explains everything in detail. Okay, if you have a model, okay, if you have a data set like 100 with 100 data points, we can have a model with like 99, auto 99, so that we can capture everything, right? Every detail. Okay, as for example, just like in the empire, okay, this is like a example that actually, I think this is a story appear like I forgot, it's in the like coming in a children's book or something, but it's like in an empire, an emperor asked like the cartographer, cartographer, the guy who make maps. Okay, the guys who make maps. The emperor asked the cartographer to create a map for his empire. Okay, and the emperor asked the cartographer to create that map to be as detailed as possible, so that it captures everything in his empire. So it turns out that map is of size of his empire. It's huge. Okay, it's so big, like it's as big as his empire. So let me ask you this: if you have such a map, is it going to be helpful? No, it's too big, right? Nobody use that such a big map for direction, right? If you have a map this big, you use that for correct direction. That's reasonable. But if you have a map that's like as big as this house, can you use that for direction? No, right? You just it's impossible for you to navigate by that map. It's too big. Not mention like the map is as big as the whole country. That's useless, right? That's useless. Okay, so same thing here. Okay, you don't want a model so complicated that it captures everything. Okay, because you don't want to recreate the noise. The noise is not what you want. Okay. But on the other hand, remember this part. Okay, if the parameters in your model is too few, okay, the model may not be complex enough to capture the signal. Okay, if that happens, we call that your model is underfitting. Okay, that's opposite of overfitting. But basically, okay, for example, let me use this example. Okay, we see the model of order 0 represent the average of those data points, right? Well, but it really doesn't give you much detail, right? Only the average, but nothing more. And the R² value is crazy. I mean, it's 0. Okay, so it's not that useful, right? It's really not that useful. So this order 0 model, obviously we have underfitting here. Okay, we have underfitting. So we don't want overfitting, obviously. We don't want underfitting either. So that's what I meant by it's important to find that sweet spot. You want a good level of complexity, not too much, not too small, just right level of complexity. Okay, so that's why this question is difficult, and that's why we need model comparison, because we may need to create several models of different complexity and see which model is better. Okay? So another way to describe this trade-off between the complexity and accuracy is called variance and bias. Okay, the variance is like the bias is the result of model with low ability to accommodate the data. So if your data has a low complexity, for example, like the model with order 0, okay, it really doesn't have enough ability to accommodate our data set. So that's called high bias. Okay, so high bias can cause a model to miss relevant pattern and lead to underfitting. So another factor is called variance. High variance is a result of a model that has high sensitivity to details in the data. So the model is very flexible. But when you have a high variance, the model may be too much accommodating, so that it can not only learn the signal but also the noise, which as a result will lead to overfitting. Okay, so this is another way to say the trade-off between the complexity and the accuracy. I mean, we can rephrase this as the trade-off between variance and bias, but they pretty much means the same thing. Okay, so we want, this quote is from Einstein. Okay, things should be as simple as possible, but not simpler. This is a sentence. The sentence from, said by Einstein. I mean, he's obviously is a famous guy, right? And you can see that this sentence capture, okay, exactly the meaning of what we are talking about. We don't want underfitting. We don't want overfitting. We want something in between. Okay, that's exactly what the meaning of this word. So in the slide 25, the order 0 model is the one with the higher bias, okay, because it's biased to return a flat line, okay. So yeah, I think I already mentioned that, okay. So okay, so a model with high bias, a model with more prejudice, okay. This is just like you are trying to use anthropomorphization, okay, 拟人化, just kind of like treat the model as a person, okay, because prejudice is like used for some people, okay. If you have prejudice, it means like you have like your opinion is not correct, something like that. Or more inertia. Inertia is like from physics, okay, from physics. So inertia means like 惯性. Okay, 惯性. If you know a little bit about physics, I mean, you guys have taken like physics from high school, so you know what inertia is, right? So with a high bias, it's like prejudice or more prejudice or more inertia. Okay, so while a model with high variance is a more open-minded model. So model is, again, this is like we try to treat a model as a human. Okay, so we say it's open-minded, but you get an idea. Okay, so it's more so. If it's too biased, then you are ill-equipped, to accommodate new evidence. But if a problem, if the model is too open-minded, then you end up believing like a nonsensical stuff. Okay, so just like a person. Okay, a person cannot be too prejudiced or it cannot be too open-minded. It means you have to be, somewhere in the middle. Okay. So that's like, again, this is just to describe the bias variance trade-off, okay? So in the previous example, it's more or less easy to see that the order 0 model is very simple. Order 5 model is too complex, okay? But what about the other two? What are the other two? The linear model and the quadratic model, right? Okay, so to answer this question, we need more principled way of taking into account the accuracy on the one side and the simplicity on the other. Okay, so that's where the model comparison come into play. To do so, we will need to introduce several new concepts. Okay, the first two are within sample accuracy, and out of sample accuracy. The within sample accuracy is the accuracy you measured from the training data. Okay, and out of sample accuracy is the accuracy you measured from the data that is not used in the training, for the training. We can say it's test data, something like that. So obviously, okay, the out of sample data, accuracy is a lot more important than within sample accuracy. Okay, we want the data to we want the model to perform better for the samples that are not in the training data. I mean, we already know the training data set, right? So if you just use the training data, I mean, again, you don't need a model. You just the result is already there, right? So you really don't need a model to answer any question that comes from the training data. What you need is, what you need a model to answer is the out of sample question, the sample that comes from outside of the training data. Then you need the model to answer that. So that's normally what we want the model at the first place. So this out of sample accuracy is actually more important. Okay. So however, generally, there is a problem with this. We need to be able to afford leaving aside a portion of the data, not to feed the model, but to test it. So that's where, we normally want to divide the data into multiple portions. Okay, part of it to use for the training data. The other part we want to leave it for to test the accuracy. Okay, we want to leave it as like a out of sample data to measure the accuracy of the model. Okay, but this is very expensive. Okay, because I want you to be aware. Okay, in deep learning or in other machine learning paradigm. Okay, it's common, it's natural to divide the data into maybe training data, validation data, and the test data. This is very common, very common. But this is not that common for Bayesian data analysis to do that. Why? Because the data, the size of the data that you use for Bayesian data analysis is normally a lot smaller than the size of data you use for deep learning or like a machine learning. Let me put it this way, okay? If you use a data set for Bayesian data analysis, normally the size of data is like within tens or hundreds. Okay, and if you want to use machine learning to do the problem, the size of the data set is normally like thousands. Okay, thousands. Okay, to like maybe tens of thousands. Okay, but for deep learning, you definitely need the data set to be higher than tens of thousands. So the problem that you apply, the approach, okay, is different. Okay, different problem require different approach. Okay, the size of the data set is an important key. Okay, to identify like a right model to use. Okay, if the size is small, well, you don't want to use machine learning. You don't want to use deep learning. Okay, because obviously it doesn't work. Okay, but but at the same time, because for Bayesian data analysis, because most of the time, the size of the data is so small, it's not affordable to divide the data further. Okay, we say, we break. We just leave maybe 20-30% data for test purpose. Well, in the other area, okay, for the other approach, that's probably possible because of the size of the data set. But for Bayesian data analysis, this is going to be a problem. Okay, this is going to be a problem. So to fight with that, how do we fight with that? I mean, we want to use all the data to train the model, as much as possible, at least. Okay, so how do we do that? There are two methods. Okay, one is called cross validation. The other one is information criteria. Okay, the cross validation, you divide the data set, the whole data set, into k subsets, and then you do the things like you try to train like multiple models, actually k models to be exact, and then you use these k models, the average of this k model, I mean, to see the accuracy. So that's like how the cross validation works. I will explain in more detail, okay, shortly. And the other is called information criteria. This is like you don't break it into like a training set and test set. Okay, you just use the whole data set to do the training. But after that, okay, you will try to discount. You'll try to discount the accuracy, or you discount the in-sample accuracy to approximate the out-of-sample accuracy. Okay, so we are going to talk about these two things. Yeah, I hope to cover cross-validation and at least part of information criteria in the final, but that's about it. I mean, I don't think we can finish everything anyway. Okay, and also as I said, like a lot of this is they are very dry, so I don't want to bore you guys to death. Okay, for those dry material anyway. Okay, so what is cross validation? The cross validation is probably the best to be introduced by this figure. So say this is the data set. Okay, and here we try to break it into k portions. Okay, and each portion is roughly the same size, with similar property. Okay, for example, if you have like different categories, different classes, you want to leave like the each class to be about the same distribution as in each portion. Okay, each portion. I mean, for example, like say the whole data set, you have two classes, and the first class is a ratio has a ratio of 2. The second class has a ratio of 1. Okay, the first class, the second class, the ratio is 2 to 1. Then for each of these k subset, you also want to maintain that ratio, 2 to 1, 2 to 1, and you just draw the sample randomly from like different classes. Okay, so anyway, so you form this k subset. So the first round, you use the first subset as a test data set, and use the remaining data set as the training data set, and you get a model A1, right? And the second round, okay, you use the second subset as a test data set, and the remaining data set, the blue one, as the training data set. You get the result, I mean, as A2. This result, okay, this result represents the accuracy of this test data set. Okay, this A1 is the model you obtain from this training data set, and then you use this test data set to see the accuracy. That's A1, and so on. And the third round, you use the third subset, okay, as a test data set, and the remaining data set as a training. Okay, so you can do this for obviously k rounds, right? And then your accuracy, okay, will be approximated by the average of this k, AKs. Okay. So this is called the K-fold cross validation, where this K represent how many subset you divide the data. Okay? If you divide the data into 10 subset, then you need 10 runs. That's called tenfold cross validation. Okay? So obviously, cross validation result in more computations, right? I mean, if you don't divide the data into so many subsets to do the K-fold cross validation, you only need to compute one model, and you only need to compute one accuracy, right? But now you need to do these K runs, and in order to approximate the out of sample accuracy. Okay, so this the cross validation is a very simple and useful idea. Not only we use that in the Bayesian data analysis, actually this technique has been applied to machine learning in general very, very often. Okay, so so keep that in mind. Okay, this is like a very well-known approach in machine learning field. Okay, and also okay, some people, okay, feels like there's one more thing. Yeah, there's one more thing. Obviously, okay, if you go extreme, okay, say you have like 100 data points, okay, if you go to the extreme of this approach, you could, for each data set, you have only 1 point. You have only one entry. Okay, and you use rest of the data set for training, and use that one particular data set for testing. Okay, and obviously, okay, if that's the case, then the K becomes like as large as like the size of data set, right? Okay, but okay, we normally call that approach, okay, as leave one out cross validation, LOOCV. Okay, but obviously, okay, if you use like this approach, you need to train so many models, right? You need to train so many models. I mean, as many as like the size of the data, training data. But so sometimes when doing LOOCV, the number of runs can be less than the total number of data points if we have a prohibited number of them. So if the data set is too large, okay, we probably only want to try to do it like say like if the data set is 100, we don't want to do like this thing 100 times. We probably do it like maybe 30 times or something like that. I mean, we get all these. The purpose, what is the purpose? What is the K-fold cross validation? The purpose of K-fold. The purpose of K-fold cross validation is to approximate all of sample. Okay, so if you already collect like maybe 30 rounds from the LOOCV, okay, that average may or
actually it's not a free sample actually, but you try to do a discount from that. And that discount is actually derived from information field. So mathematically, it's very complicated. So the only problem to do some just tell you how to use that. So we are not going to details of how that is. So, and to be more specific, what I'm going to do is that I'm going to just talk about one. There are so many. For example, here there's a law that this one has this is not so if you were to measure how well now fit the data, you can fit it. Okay. So this one, okay, is programming between the data and the precision. The programming error, I think everybody knows that, right? Okay, this is not one of the many for the square error will show that equal if you do not cancel out each other. So why do you able to do this square? It's just because of the you want the error. For example, if this is the error, possibly the other one is negative error. If you don't want to simply add up, this is like because they will cancel out each other, right? So we use square so that everything tends to be positive, right? That's perfect. The errors do not cancel out each other. So, the second thing is that we want the errors to be as small as possible. So we want to penalize the bigger errors. When we do a square, like the obvious is that the bigger errors will get much higher value, right? So because of these two reasons, the mean square error is first. So another way, okay, there are other ways to compute similar problems. For example, you can use the absolute value. The absolute value, obviously, errors will not cancel out, right? But it will not be able to penalize larger errors. Okay, that's and the more general notion, okay, is to compute the log likelihood, which is the log likelihood. So when the likelihood is normal, okay, it turns out to be proportional to the probability. For the historical reason, we don't use this term, okay, for model measures. Instead, okay, we define this one as a previous. Okay, so it's negative 2 times this okay, so because we have a negative 2 attached to it. And previously, okay, this one smaller than Z node, right? So it's smaller than, okay, it's smaller than that. But now, because we have negative 2 attached to that, divide by this by negative 2. So the larger element, okay, the difference is the Asian and the non-Asian. The difference goes up. So the lower field, the higher the magnitude. Okay. And the higher the the lower the field, the higher, actually, the higher likelihood, not likelihood, the lower the field, and the higher the agreement of the model prediction and the data. So it's better. So we want the lower field. We want the lower field. The field measures the reading sample accuracy, and the complex model will generally have a lower field than simple. Because after all, we remember field as a compound model. So this category from here, all these tools are computing the sample accuracy, right? Okay, so we first calculate that, and then we try to apply analyzation first. So pretty much all these information criteria have something to do with the form of this video. Okay, so this is one of them. Okay, called a type information criteria. Really, AI, but you can see this form is very close to the distribution video. So as I said, there are so many of them. I mean, I will not go into the details. And also, okay, the important thing is, remember I said we will have a penalization term, right? To adjust, because like this portion measure the in-sample accuracy, right? And I said the in-sample accuracy is normally too high, right? It's normally too high, so which is not, it doesn't represent all of them. Okay, we want measure all of them. Okay, so because this first term normally represents in-sample accuracy, so we have second term. This second term is 2 times PAID. This P, okay, is like the size of the number of parameters. Okay, the number of parameters. So, the second term penalized complex model. The more complex the model, the larger this term. Okay, so the resulting AIC is going to be larger. Okay, the larger the AIC, okay, the higher, this is sort of representing the median, right? So we want, remember, we want the lower median, right? The lower median represents better model, right? So this penalized term will increase the median. Okay, so that's the criteria. That's the information criteria. I'll take the information criteria. I just use this to as an example to show you the general form of information criteria. Okay, it's always a term. internalization curve, okay, which is relevant to the size of the model, complexity of the model, so the number of factors of the model. Okay, and the larger the model, the higher the element. So that's something I want to do. So I will not go into the details. It's not the main part of the process. So, okay, let's take a look at that. We come back. We'll talk about familiar analysis, which is really the one.
Okay. Yeah. Well, I didn't hear the bell ring, but yeah, it's about time. Okay. So today is actually the last lecture of this class for this semester. Okay. Of course, like we will still have like the final exam next week and the term project presentation the week after next. Okay, and yeah, so that's and today, okay, we are going to the material that we are going to talk about today. Part of them, okay, will be covered in the final, but you know, the other will not. Okay, because I kind of feel like some of those details are not are too much detail and require a lot of memorization, which is not what I like. Okay, so I mean, if you want to do that, I mean, use those like a concept, you can always check back. I mean, the textbook at a later time anyway. So yeah, remember we talked about the this thing. Okay, model is not the real world. Okay, all models are wrong. Okay, we are only we only want to find the model that's the best or the better. I mean, probably I shouldn't use the term best. I mean, if you have multiple models, like which one is the better one? Okay, I mean, when I say a better one, I mean like it can explain the problem, it can explain the data better. Okay, so that's like the main topic, the most important job of the model comparison. Okay, so we talked about that we could use posterior predictive check, okay, to compare models. Okay, and we saw the example like this. Okay, we have a bunch of points from a CSV file actually. Okay, and then okay, we intentionally create two models. The first one is a linear model. The second one is a polynomial model. Okay, quadratic model. Okay, the first one is called model L. The second one is called model P. Okay, P stands for the polynomial. Okay, and yeah, this type of stuff, I mean, we have been discussed those many times. So I will not go into a detail. I mean, on how to construct these two models, because these two models are really simple. Okay, but if you put them, you know, on this data points, okay, you try to visualize the result. Okay, you will find that okay, the orange one is the linear model, and the green one represent the quadratic model. Okay, keep that in mind. Okay, keep that in mind, because later on in all the figures, you will have to remember. Okay, the orange one represent linear, the green one represent the quadratic. Okay,
So you can see on this figure that, you know, both model looks fine, right? Both model looks fine. I mean, they sort of explain this data pretty well, right? I mean, visually speaking, okay, visually speaking. So, so what do we do? Okay, one thing we can do is that we can plot the mean and the interquartile, okay, interquartile range for these two models, as well as the real data set, okay, real data set. So the result turned out to be like this, which really doesn't give us any hint, okay, as to like which model is better. I mean, well, obviously they have the same mean, because remember that, okay, we actually normalize, I believe, like we centered the data set before we create a model. So that's why you see that, you know, the data as well as linear model and the quadratic model, the mean are almost all zero. Okay, this is like because this is the result of the centering the data point. Okay, however, when you check the interquartile, if you know the interquartile meaning, okay, basically, you know, the first quartile to the third quartile, okay, the third quartile, you know, this is the first quartile. This end represents the first quartile. This end represents the third quartile. Okay, 四分位数啊，四分位数。Okay, 第一个四分位数，第三个四分位数。Okay, yeah, that's one way to see like how you know, data scattered in the model. Okay, so if you could use this result, okay, to identify which model is more resembled to the data, then it's great. It's great. I mean, we could have just used that model. Okay, we could just consider that model to be a better one. Okay, but unfortunately, I mean, for this particular example, okay, remember this one, linear model, and this one is a quadratic model. I mean, both interquartile range are similar, okay, to the interquartile range of the data points, right? I mean, at least, like, again, visually speaking, the difference is very minor, right? So what do we do? So obviously, this one doesn't help that much. Let me repeat, okay, if this one work, okay, we will just use this as a criteria to determine like which model is better, okay? But unfortunately, when this does not work, what other tool can we have? Okay, what we can do is that, okay, we can plot the dispersion of both mean and the interquartile range as opposed to their mean values. So we can sort of like, because remember, okay, when you get a model, okay, of course you also get the posterior for all the parameters of the model, right? You have the posterior, okay. It's not just like a model and the sum result. No, it's a complete you know, probability distribution, okay, of all the parameters, okay. So what you can do is that, you know, because it's a distribution, you can, you know, keep, you know, extracting samples from a model, right? This one we can do that, right? For example, like we have a model, okay. We try to use the posterior predictive check, okay,
if we call that once, we can extract some sample from the model, okay? But you can call its function multiple times, and as a result, okay, you can see like what we meant by the dispersion of mean and the dispersion of the interquartile range. Okay, I mean, for model we can do that because model, I mean, represent certain distribution. Okay, certain distribution. I mean, it's a posterior distribution, but the most important thing is we can we can obtain the samples from this distribution. Okay, so here's the thing. Okay, we can draw this figure. This will be a more interesting figure. Okay, this shows the dispersion, or I should say distribution of a number of samples you obtained from the posterior distributions. Okay, because each time you get some sample from the distribution, you get a mean, right? You get a mean. So you can do this multiple times, and that represents the dispersion, okay, or like distribution of the mean. So again, the orange one represent the linear model, and the green one represent the quadratic model. Okay, so let's not look at this one first. Let's look at this figure. Okay, and the center one, this 0.0, what is this? Okay, that's like the mean of your data point. The mean of the data point, because you only have a fixed set of data points, right? The data point is not a distribution. Okay, the data points are not a distribution, so you cannot like do the mean and get of the data point and get a different value. That's impossible. So you can only get one mean from your data. Okay, which is depicted here. Okay, so you have only one value for that, but for the two different models, because what we have are the posterior distribution, so we could do this multiple times, and we can draw this figure. Okay, so of course, what we want is that this distribution, okay, the distribution of the mean should be, centered at the 0.0 as much as possible, because after all, okay, the true mean is 0, right? So let's have a look. You will see like let's not look at this one. Okay, you will see like both distributions look like they also centered at the 0, right? Pretty well. So again, this may not be a good indication. May not good, at least like a left-hand side. Okay, the difference of two models is very tiny. It's very minor. Okay, so how about let's look at the interquartile range. Again, because the data points are fixed, so we only have one interquartile range value. Okay, that's a fixed one. That's a fixed one. Okay, so that range, okay, the range basically is just like a third interquartile minus subtract the first interquartile. Okay, that will be a value for that. Or put it another way, it's like this value subtract that value. That's the interquartile range, right? So we only have one value for the data points, okay? But how about these two models? Okay, because we can sample many times and draw the distribution of the interquartile range for each set of samples. Okay, so it turns out that, okay, when you draw draw the lines for these two models, okay, the orange one looks like this, and the green one is a quadratic model, looks like that. Obviously, okay, both models are not centered to the true interquartile range that well, right? There's a small bias here, but obviously, okay, the orange model, the linear model, has a smaller, or I should say like the linear model, the orange one, is closer. The center of the linear, the distribution of the linear model is closer to the true interquartile range, right? The center of the orange line is closer to the true interquartile range than the quadratic one, right? So this, okay, is a deal breaker. Okay, we could use that to determine which model is better. Okay, which model is better. So then let's look at this p-value. Okay, this p-value. Okay, what does this p-value stand for? I mean, this p-value, the definition is very similar to what appear in the traditional or frequentist statistics. Okay, let me first tell you the meaning of this. How to use this p-value. I mean, by the way, when we say the p-value here, what we are talking about, okay, although the name looks the same, but this p-value that we are talking about, this is actually the Bayesian's p-value. Bayesian p-value. Okay, as opposed to the traditional p-value in frequentist version. Okay, so even though the definition looks similar, very similar, but they are different. I will explain the difference, in a minute. But now let me explain. Okay, how do we use them? Okay, use this p-value. Okay, if the data and the simulation agrees, okay, we should expect this p-value around 0.5. Okay, so this is a good indication. It's a good indication to tell us, whether or not your distribution is centered at the right value. Okay, I mean, in this particular example, that right value is the true data, okay, obtained from the true data. Either it's a mean or it's an interquartile range. Okay? So if it's deviate, if the Bayesian p-value deviate from 0.5, okay, then we are in the presence of biased posterior predictive distribution. So, okay, if you look at the p-value, you will see, okay, the first one, the linear model has a p-value 0.5 for the mean, and the quadratic model has a p-value 0.51 for the mean. The difference is very minor, just like what appeared in the figure. Okay, but on the right hand side, okay, for the interquartile, okay, the p-value
for the linear model is 0.37. It shows a little bit bias, right? But for the quadratic model, the p-value is 0.23. It's even worse. So if you want to use, you want to justify which model is better numerically, okay, quantitatively, okay, then this Bayesian's p-value could be a good one to use, okay, along with the posterior predictive check, okay. So now let's look into what this p-value stands for, okay. So the p-value, its definition, okay, is okay the probability of like your simulation result. Okay, this t stands for any index. Any index. It could be mean. It could be interquartile. It could be any other summarized statistics stuff, such as like the standard deviation, or anything you can compute from a distribution, or from from your data, basically. Okay, as long as it's a one value. Okay, so it's a probability of the index you compute from simulation is greater or equal to the probability of the observed. This observed is the true data. Okay. Given y is the data. Okay. So in the examples that we have seen, okay, the t, okay, has been used for mean and the interquartile range. Okay, and okay, you may wonder, like because like earlier, okay, when we talk about the Bayesian data analysis, okay, I keep telling you guys that, well, the frequentist statisticians, their work, okay, are not that. I should say there's some issues. Okay, of course they will argue differently, but I would say from the Bayesian's perspective, okay, the frequentist, biggest problem for frequentists is that they use p-value and they use null hypothesis, test. Okay, so you see, how come? I mean, we are using we are also using the p-value here. I mean, so what's the difference? What's the difference? Okay. Actually, let me tell you this. Okay, just by looking at this definition. Okay, this definition, okay, of the p-value is pretty much similar to the definition of the p-value used by frequentists, okay, by the traditional statistics. Okay, they are similar. So what's the difference? The difference is that for frequentists, okay, the way they calculate this thing, they draw samples. When they draw sample from the true distribution. Okay, for example, like when they remember what I told you, like I don't know if you guys remember. Okay, but anyway, okay, when the issue with the p-value for frequentists is that when they try to calculate this p-value, okay, the way they draw samples from the true distribution will affect the computation of the p-value. For example, like at that time, I believe I was using like the coin flips. Okay, so for example, like so now it's the data is like this. We have like okay, we have collected 10 coin flips, and we have 3 heads and 7 tails. Okay, so I want you to compute the p-value from this data set, from this data, and you say, okay, so good, but in order to calculate the p-value, okay, for frequentist, I need to know how this data are collected. Why? Because let me give you two scenarios. Okay, the first scenario is that, okay, I just don't care, the result. Okay, I just throw 10 times coin flip and collect the data. It's like that, right? 3 heads, 7 tail, right? So regardless, the result, I just throw the coin 10 times. Okay, so the stopping criteria for my data collection is throw the coin 10 times. Okay, and then okay, you can easily compute. I mean, you guys have taken like a probability class from high school, so like okay, based on that, you can compute. Okay, for 10 coin flips, the probability of getting 3 heads, 7 tails, right? Everybody can do that, right? That's not a difficult question to ask, right? Okay, so, but if I give you a second scenario, okay, this time, okay, the data collection is done like this. I flip the coins until I get 3 heads. I flip the coin until I get 3 heads. And it happens that, well, I throw 10 times, and the 10th time I get a head, the 3rd head. Okay? And the previous 9 times I get, well, 7 tail and there's 2 heads. Right? That's also one way to collect data, right? Right? That's also one way to result in 3 heads, 7 tails, right? But the probability of getting 3 heads, 7 tails will be very different, right? Will be different, right? I mean, if you know how to calculate the probability, right? So because of that, you can see, okay, how data is collected will have the impact to the probability distribution. Okay, and as a result, okay, it has impact to the p-value for the traditional frequentist. Okay, so that's why, as I say, if you want the frequentist to compute the p-value, that guy will ask you, okay, back, how do you calculate your data? Because without knowing that, he doesn't know how to calculate it. Okay. However, in a data science, point of view, okay, a lot of time, okay, when you get a data set from maybe internet, you have no way of knowing how the data is collected, right? You have no way of knowing that. Okay, so that makes frequentist approach problematic, to say the least. Okay, because there will be obviously certain issue when they calculate the the p-value because they have to assume how the data was collected, but it could be different. It could be different. It could be wrong. Okay. But so how about the Bayesian's p-value? The Bayesian's p-value were calculated directly from the posterior distribution. Okay, because it's drawn directly from the posterior distribution, which obviously like a frequentists do not have access to the posterior distribution. Okay? Okay, so because the Bayesian's p-value, the difference is that we, for example, okay, remember what I told you? Okay, I say, okay, for this mean, for example, okay, we actually get like a multiple set of samples from the posterior in order to calculate this dispersion, right? But this can be done by Bayesian data analysis, but this is not available by the frequentist. Okay, and also when we do the data analysis, okay, when Bayesian data analysis is done, okay, if you check the steps of Bayesian data analysis, what is important is the prior, the likelihood, right? We don't care, we don't assume particular data collection. Okay? So that's why the result of this p-value is independent, okay, from how the data is collected. There are other issues. I'm just trying to tell you, okay, based on one most obvious problem of the traditional frequentist p-value. There are other issues as well. Okay, but I will not go into the detail of that. Okay, after all, you guys probably do not know much about the frequentist p-value. That you probably just know a little bit. Okay, so same thing. Okay, for the null hypothesis standardized test. Okay, because they are built. Okay, p-value, NHST, they are built on the same ground. So both are flow, to say the least. Okay, I mean from the Bayesian perspective, of course. Okay, so here, okay, I just want you guys to understand. Okay, the Bayesian p-value could be used as an indicator. Okay, to identify which model is better. Okay. So this is like what this is, and this is this is what we call Bayesian p-value, and also why it is different from the frequentist p-value. Okay, you need to understand this. Okay, things like this. Okay, by the way, could appear in the final exam. Okay, obviously, because final exam is next week, right? Okay, so I mean the way I give the questions in the final exam, I always give like a big concept type of problems. Okay, for example, this is one of the important concepts. Okay, what's the difference between like a Bayesian's p-value and frequentist p-value? Okay, and how do we use the p-value? Okay, in Bayesian data analysis. Okay, so I think I already discussed that. Okay, so posterior predictive check. Okay, either we use plots or numerical summaries. For example, like a Bayesian's p-value. Okay, either combination of both. Okay, very flexible ideas. Okay, they are flexible idea for the model comparison. Okay, so this concept is general enough. Okay, to let us like come up different ways to explore posterior predictive distribution and use whatever fits to tell a data-driven story, okay, including but not restricted to model comparison. But of course, in this chapter, we are primarily focused on the model comparison. So in the following material, we are going to explore other methods, okay, to compare models. So, the first tool that we can use is posterior predictive check. The second type of tool, okay, you know, it has a big set of stuff that we are going to talk about. I mean, but there are some principles that I would like to sort of like inform you guys, okay, before we go into detail of like different tools, okay. So when choosing among different models, okay, there's an important guideline, okay, known as I think this is called ACME, okay, Archimedes razor, okay. I don't know how this name is obtained, okay, because razor normally is for shaving the beard, something. But obviously this is not the way of this word. I mean, explained here, okay. Basically, okay, this Archimedes razor, okay, state something like this, okay. If we have two or more equivalent explanations for the same phenomenon, okay, if you have more than, two or more than two explanations for the same phenomenon, then we should choose the simpler one. The simpler explanation for a phenomenon is preferred. It's preferred. Okay. Second, given simpler models, okay, are easier to understand than more complex models, we should keep the simpler one. So simpler models are preferred over complex models. Okay, so the first statement tells you simpler explanation is preferred over the complex explanation if they have the same, if they are sort of have the same explanation, ability to a certain phenomenon. Of course, this is the assumption. Okay, if they are roughly have the same expressive power to a phenomenon, then you should choose the simpler one. The second one tells you, okay, if two models performs roughly the same, okay, then you should pick the simpler one. So by the way, if we apply the Occam's razor, when we are at this figure, we actually can already have a conclusion. Why? Because linear model is simpler than the quadratic one, right? Linear model is simpler than the quadratic one. So, well, I mean, because they roughly have the same expressive power, they roughly can explain your data point at about the same level. So we should pick the simpler one. So you can pick the linear model here, right? Which happened that, okay, you can see, well, the simpler one is better. Okay, when you have a more, complex analysis that actually, fit like that's like happen to be the same as like what Occam's razor suggested. Okay. But anyway, this principle is very important. Okay, another justification is based on Bayesian statistics. For example, like a Bayesian factor. Yeah, we are going to talk about Bayesian factor, but we may. I think at some point I have to draw a line. Okay, to stop because like there are a lot of like material that are pretty dry. Okay, from in between. I mean, before we cover the Bayes factors. So I will try to cover Bayes factor, but I will tell you, you know, where the final exam will, you know, will be covered. Okay, I mean, but not the Bayes factor. Okay. So another factor that we take into account for model comparison is accuracy. Okay, so how well the model fits the data. Okay, basically. Okay, so in the previous chapter, we already used like a, you know, coefficient of determination R squared. Okay, which basically explain like the accuracy in certain, you know, it sort of explain the accuracy. So we want the model with higher accuracy. So you know, the R squared value, okay, is one of the such indicators. Okay, if you already forget what R squared is, I mean, remember I show you many figures that has like different R squared values. Okay, for X and Y. Okay, the correlation between X and Y. Okay, if you don't remember that, I mean, check. I think like last chapter or the chapter before last. I forgot. But yeah, we talk about this. So intuitively, it seems that when compare model, we tend to like those that have high accuracy and those that are simple. But here, okay, this you know, so we have two criteria here. One is accurate, one is simple. Okay, but these two may not coexist. These two may not coexist. Okay, so what should we do if the simpler model has the worst accuracy? Or more generally, how can we balance both contributions? Actually, as I said, like normally simpler model tend to have you know, lower accuracy. Okay, or let me put it another way. Okay, the model, okay, will become more and more accurate when you increase its complexity. But up to a point, when you increase the complexity, the model's accuracy no longer will no longer be it will be actually so it's something like this. If this x-axis represents the complexity of model. Okay, of course the larger the x value, okay, the more complicated the model is. The y represents the accuracy. Okay, again, the higher the y, the more accurate it is. Okay, what you normally see is like this. Okay, so there's like a sweet spot that we want. Okay, if we are here, we have some issue. We call this thing as underfitting. If we are here, we call this issue as overfitting. Okay, so this is it turned out to be a very, very important concept in machine learning. Okay, in machine learning. Okay, so how do we balance the accuracy and complexity? Okay, so we are going to discuss this idea, okay, of balancing between the two contributions, the accuracy and the simplicity. Okay, so this topic is more theoretical than the previous one. Okay, but we are not going to get into the mathematics part of that. Okay, we are going to use just like code, figures, examples. Okay, to help us understand. Okay, this intuition. Okay, of balancing these two things. Okay, so we are going to begin by fitting increasingly complex polynomials to a very simple data set. Okay, so here we go. Here we have like 1, 2, 3, 4, 5, 6. We have 6 points. Okay, 6 pair of x, y values. Okay, so this is a very, very simple data set. Okay, and here, okay, we try to create, I believe, like 4 models. Okay, we create 4 models. So in this figure, okay, you see this point, this point, this point, this point, this point, this point. We have these 6 points, right? And then you can see that, okay, we create 4 models. The first one model, the order is 0. R squared value is 0.0. Remember, R squared represent the accuracy, right? R squared represent the accuracy. The higher the R squared, the more accurate your model is. Okay, so order 0 obviously has a very bad accuracy. Okay, so order 1 is that linear model. Okay, which gives us that. Oh, by the way, order 0 is that orange one. Okay, because order 0 basically just a constant. Okay, that constant is represented by this orange line. Okay, and that orange line actually will be, okay, if you try to use such a model, okay, to feed the data, what you are going to get is the average of the data. Okay, or put it another way, the average of the y. Okay, that's very intuitive, very natural, right? Obviously. Okay, and order 1 represent the linear model. Okay, we talk about linear regression all the time. So the green line represent that linear regression result. Okay, and order 2 is like a quadratic model. So it's represented by the I believe it's a red line, and order 5 represent. I mean, is we have like if you try to write down a model with order 5, you will see that you have actually 6 unknowns, right? 6 unknowns, and obviously, if you try to fit a model with order 5 to 6 data points, you get a perfect fitting, right? You get perfect fitting. So that brown line gives you a perfect fitting of those 6 points. So and you get R squared to be 1. It shows you that the accuracy is perfect. It's perfect. So you say like, well, how come we don't see a drop down here? Okay, I will explain this shortly. Okay, because we are using, here the R squared is calculated. We use training data set to calculate. In that case, yeah, the R squared will keep increasing as long as you increase the complexity of the model. Okay, but and also you see like when order change from 1 to 2, you can see the R squared value also increase, right? But obviously, the increase of R squared, is much more dramatic from between order 0 and order 1, then the order 1 and the order 2, right? Okay, so R squared value, when you increase from 2 to 5, the only difference is 0.02. There's not much difference in terms of like accuracy improvement. Okay, so obviously there's still a sweet spot here. Okay, the improvement obviously is much better for order 1. And also, when you look at this data point, you can obviously see that this data point, okay, if you are going to have more data points, most likely those data points will appear somewhere near this line, right? So you can probably tell that, okay, just by this visual result, that, okay, either the linear model or quadratic model will perform better when you have more data points. Or put it another way, when you predict the other values, okay, because obviously you train the model based on certain data set, but eventually this data set is going to be used for prediction, right? Which will be used, okay, this means you are using this model for the data points that are not seen in a test data set, right? In a training data set, right? So obviously, okay, just by the visual result, you can probably tell the model of order 1, order 2 will perform much better, okay, for the future data points. For the future data point, but we are going to, talk about this in more, numerical manner. Okay, let's take 10 minutes break. When we come back, we'll continue. Okay. Okay, so for information criteria, okay, what I really want to talk about is this one. Okay. The widely applicable information criteria, abbreviated as like a WAS-AIC, WAC. Okay, it is. You can see the form of WAIC is also like this: -2 times LPPD plus 2P WAC. Okay, so you can see that. Okay, the format is very close to the AIC. Actually, like there are so many different information criteria. As we later, I can go through them, but I don't want you guys to memorize every one of them. This is really not that necessary. And the reason I would like to make particular pick this one, okay, is because this one is actually used much more often compared with the other information criteria. Okay, so this first term is also somewhat related to the what should I say, the deviance. Okay, deviance, and the second term is again something that is relevant to the size of the model, okay, or complexity of the model. Okay, the P also stands for the parameters, number of parameters. So the more complicated the model, the larger of the second term. Okay, and for this WAIC, okay, just like the previous one, okay, we want it to be as small as possible, okay. So that's why, I mean, this term, the penalized term, okay, if the model is large, okay, you are penalized. The model is complicated, you get penalized, okay. So you know, we prefer lower value of WAIC. This is the more important. And for the detail of how this is calculated, don't worry about it, okay? Because after all, like you only need to know the first term is relevant to is okay. The second term, okay, is a penalizing term for the complexity of the model. This is what I want you to understand for the WAIC. Okay, that's good enough. Okay, and there are other, you know, you can call criteria as well, called LOO, which normally is used for the LOCV. Okay, and it's based on the Pareto smoothed importance sampling concept. But again, I don't want you to learn so many. LOO is just like a WAIC. Also, I mean, very often used. I mean, but LOO is restricted to the LOCV type of application, okay? But the WAIC is I would say it's more general, okay? So criteria such as deviance information criterion, okay, and Bayesian information criterion, okay, DIC, BIC. You know, I don't want you to memorize all of this. I mean, there are too many of them, okay? But the reason I picked WAIC, as I said, is because you are going to see more applications. So, and also WAIC is recommended over DIC anyway. Okay, so that's why we are focusing on WAIC. And if you want, okay, to compare the model with IMPC by using the WAIC, okay, there's like AD.WAIC function that is output this WAIC value, okay, and this is WAIC value, this is standard error WAIC value. This is the PWIC. This PWIC is this term. Okay, so it sort of indicates the size of your model. Okay, and the warning, okay, most of the time is 0. But when the warning is non-zero, it's bigger than 1, okay, that means something is wrong when you move into your model, okay? You move into your model. But most of the time, you won't be wrong. So, and also, I want you to understand one thing, okay? No matter what information criteria we are talking about, okay? It is used for model comparison. So, to see a value, one value for the value of WAIC for one model, it doesn't say anything. So for example, okay, this is a linear model, right? The trace. This is remember we have 6 points, and we have 2 models. Now we need to take into account. One is linear model, one is quadratic model, right? So this is the linear model result. Linear model. Is 3A 47? Is it good? No idea, because all these information criteria are used
comparison, because you don't just look at it one value and say, oh, this is good, this is bad. No, 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 no. You check multiple values. Right? You check WASD values for multiple models and identify which model has the lower value of WASD as the model. Okay? So this one, yeah, I mean, you are able to print out, okay, the value of WASD and the use of all these relative information types. Federal warning, okay, that's it. Okay, so to indicate the idea of WASD. Okay, so there are non-zero WASD is not reliable. So, since the value of WASD are always interpreted in a relative fashion, so printing out one WASD for one model is useful. So here, okay, you can see that there's another function, auxiliary function we can use, okay, for model comparison. AD.model compare, so AD.compare, we input model L, trace L, that's the linear function, model P, trace P, that's the programming model. So one is see that it's two results. Okay, so we know like with 28.75 will depend linear model, right? Linear model. I mean, this is linear model. So this 9.07 actually is ahead for this value for the comparative model. Okay, so for this particular example, quadratic model is better. Okay, because it has a lower WASD value. Remember, the lower the WASD value, the preferred, more preferred that model. So basically, the first, and by the way, okay, this one, the way this model, this result are represented, they are listed in increasing order of WASD. Okay, by default. So you can see that, okay, the first one we see is the linear model. The second one is the polynomial model, right? The quadratic model. But the first one that brings out is quadratic one. It's not a linear model. Because the second model has a lower WASD value. Okay? And the PWASD is like the example branch before model we stress. Okay? And the PWASD is the relative difference between the value. So you can see the because it's listed according to the increasing order of WASD. So this one, the first one is always good. The second one is basically the difference of these two. Okay? If you have the third one, then it's going to be the difference of the third one and the first one. This PWASD just is going to be the value of this model, the WASD value of this model, subtract the first one, the first WASD value. Okay? The difference of WASD. This way is used for model combination. You could combine multiple models to do prediction and so on. Okay, but so it will automatically compute this. Okay, for example, maybe this one is 0.7, this is 0.3. So it's like the result will be the weighted average of multi model. But for this one, you can play this one This is zero. Because the first model, okay, the quadratic model is too good. Too good. I mean, you see the difference of these two dimensional entities is so huge. So the weight of the quadratic model is dominant. It's dominant. So that's the meaning of the word. This is standard deviation. Standard error of the AIT. Okay, and then this is the difference of standard error. The error coefficient. Standard error coefficient. So because the first one is always there. This one is the difference. The standard error coefficient. Okay? And warming, I already said about warming, right? So this is like, how you use AIT. Okay? So I already went through all these topics. So this is one way to visualize the model comparison. Okay, so we can use AT.plot compare. Okay, to draw this diagram. This diagram was actually introduced by this Richard Elwin. Okay, this Richard Elwin is also a very important person in Asian development. Before Python became popular, then people tend to use what people use like code. I mean, Python is like a code platform, right? Like you can do the Python code on Linux, Windows, Mac, right? So the Python is more like a family code. But before Python becomes so popular, okay, as I said, people tend to use like before R, and also R and Python are scripting language. Okay, so they are sort of platform. But before that, even before that, okay, the spatial data analysis actually came into play in the late 1990s. At that time, what is the most dominant platform in computer, in personal computer? Windows, right? Windows. Okay, so this guy, okay, Richard McElwin, okay, this guy created a package, okay, called the WinBot. Okay, Win obviously stands for Windows. Okay, Bot is like B stands for Asia. U and the G as it is for like the central net. Okay, so central net is the fact in this package. So basically, okay, because of that WinBot, okay, package, okay, it is still available on Windows platform, but it's not that popular anymore, okay, because there are so many spatial data packages out there now. But at that time, okay, back in those days, okay, that package obviously pushed the popularity of the spatial data analysis a lot, because like with that package, you can write simple code to generate the posterior, okay, just like what we use Python okay, and so this guy is an important person, okay, that pushed the popularity of spatial data analysis. But anyway, he also wrote a book, The Physical Distinction, okay, which is also famous, but he is not as famous as the other people I mentioned, okay, such as Cruz and solar. So those two are even more important. So you got to look at it. The more important thing is happy to contribute. All that. So he proposed this video. So this video probably needs a little bit of convention. Okay, so what is this? Okay. Obviously, Model P stands for the this bar represents quadratic model. This bar represents linear model. So x-axis represents the value of linear model. Okay? So this range actually represents the error. Okay? Remember, we have this arrow, right? We have this standard arrow, right? And so this range actually represents standard arrow. Okay, and this is standard arrow. Where is standard arrow for linear model? The center one, the center value obviously for the linear. So, and you know, the lower the better, right? So this bar, this static bar represents, okay, this is the bad model. This static bar represents the bad model. Okay? So, which, as I said, is most of the time will send first step. Most of the time, but it's not always. But it's a few people because you can see this term and the Pokemon. And you can actually right? So you get an idea. So this figure is normally will get the first step. So this is this circle represents this value of the video. And the all model set the top range represents the kind of indicating the value of the feature of familiarity between that model and the top of the gray arrow bar indicating the standard error of the feature between the top range. This one indicating the feature. Of the people. So this is this one. And this one. Okay. So that figure actually pretty much captures almost everything here. So it's pretty up to what we like. We like this numerical result, or we like the visual result. So it's pretty up to you. So either way. By how much? And this is also important that you can see that in this range, does not overlap, right? If there's an overlap, then it still means that there's still like debatable which model, right? But if there's no overlap, it's clearly the model P, projected model is better. Okay? So, yeah, standard error is not overlap. Here, comment maybe we show one model. Okay? And yeah, this is about error. So I think most people too much detail. And reality will only help model selection. Red and the blue should be complete complement with conservative check. So we should use all the tools that's possible to model compare. Don't stick to only one tool. Okay? If possible, try to use the main tool to model compare. So this is something that we use. And there's a model average. Okay, you can compute the weight and you can average over model for your prediction. Like I said, so this is normal model comparison. It's more like a combined model into one. Okay, so this one, okay, this is the shear here, what that means. I think that those are very common to our speech. And when you use this is okay. So this is meant we're using a shear function of this W function. This W function is extra W. The later set more than one true and more than one arm. So we are able to fulfill this check. The one model at the same time. Together. So this one is we actually see the model and the model speed to this like that. And here we intentionally keep we have a linear model, which is represented by the original, and we have a green line, which is the red model, okay, and we have a weighted model, by the blue line, by the red line. But be careful about this particular this one, okay, is a weighted element, right? But this weighted element we intentionally make the weight 0.5. So it's more like the average of the two models. But if you want more reasonable weight, then this is the value. This is the value that should be determined. Okay, so actually the quadratic model has a dominant weight. Okay, but so you say, why don't we use that weight in that example? Because if you use that weight in the example, basically the combined model will be exactly the same line as the quadratic one, right? When you draw it, it doesn't show any just show two lines. There's no third line here. So the author is itself is using this by to create combined model. But you get the idea, okay? So if we want to use the right weight should appear here. Okay, we should use this weight instead of the weight model. So the last one, okay, is another is Euclidean model, right? So we can put this condition, okay, into the model trained on this particular formula. This base theory obviously is based on certain model. Okay? And then, okay, the third denominator is known as marginal likelihood. And then, basically, okay, the base vectors are this defined. The marginal likelihood the ratio of marginal likelihood of different models. Okay, so this base vector, okay, when base vector is greater than 1, model 0 explains theta only. Okay, there's actually a scale. Okay, here. So if the ratio is from 1 to 3, okay, it's an example. So this is better, but not that much. Okay, but if the ratio is 3 to 10, it's moderate. Very short. Greater than 100 is true. Okay. So basically that's our number. Base that. But I won't tell you this, but I will not put that in the final state. Okay. This is okay. For this chapter, okay, everything up until the K quantization and the frequent out quantization, as well as the stuff that's relevant to WAIC, okay, may appear in final state. The other is the main criterion for base vector. I want you to understand there are so many different tools to compare between different models, but I don't want you to memorize or too much there. Okay, so that's pretty much about it. I will stop this graph. Here, okay, because the other, I think that there are other, for example, the base vector, there is another thing that's called posterior arc, which is I think those are too much detail. As long as you can understand some of those tools, I think that's reasonable. And one more thing, okay, to the final exam, okay, the final exam is not overbooked, but it is, you can do it in one page cheat sheet, just like I usually do for the final exam, the final subject. Okay, so you can put whatever stuff in that cheat sheet, okay, but just one page. Okay, you don't print a page of figures, so that's what if you don't ask me like, can I do it like two-sided? I will not share that much detail, okay? You just write your stuff. That's your business. But don't bring in one book. Don't bring the whole book of notes. Like, then they will be your whole book. I don't need anything. Okay? So that's about it. Any questions? Any questions for the final? You guys have seen the simple final exam, right? Okay, so I think you will see that for the problem I assigned for those exams, I tend to assign like a concept. Okay, so really like those concepts are like if you take this class and I expect you guys to understand. How it I'm not asking you to remember every time you get me. That is why I want you to do the cheat sheet. So if you know, too much detail for the family. You know, I haven't started, you know, designing the plan yet. Okay, I believe that the time this weekend. Okay, so together. Okay, so that's it.